And I'm live. That is cool. Today is 4th of September 2025, Thursday, and today we are going to do some combinatorics. We have done all the questions at 1400 level. Wait, let me stop the video here, and yep, a new page. Yep, at in CP31 at 1400 level, we have done all the questions, all of these, so that is cool. But now, before breaking on to the 1500 barrier, we have to first read some theory. And I think in Competitive Programmer's Handbook, the things that we are lacking at are bit manipulation. We have to go through this also once, at least once, and also range queries. There are segmentaries. I think we might need them at 1500 level. 1500 rating questions. Yeah, range queries, bit manipulation, and also a few graph things. Tree algorithms, spanning trees, shortest path graphs, directed graphs, strong connectivity, tree queries, paths and circuits, flows and cuts. Okay, we can go through these slowly, but we can go through these 3 chapters at least, right? Okay, these 3 chapters here in graphs and bit manipulation and range queries here. And for today, combinatorics. My combinatorics is very bad. So we have to work on that. Combinatorics and also probability. My probability is also very bad. So we have to work on probability. Maybe we will do game theory also. I don't know. But for today, combinatorics, it is. Yep. Combinatorics. And okay, in combinatorics, first we have a basic description. And then we have binomial coefficients, which is going to be cool. And the main thing is that is clarity. Once we go through a formula or we see any formula, we have to know why that formula works or why it is the way that it is, like we did with number theory, like Pascal's triangle. Why is Pascal's triangle cool, right? And then okay, this is also inside binary coefficient. Then we have Catalan numbers. I have seen a few videos on Catalan numbers, so this is going to be cool. And then we have inclusion exclusion. And in inclusion exclusion, I remember there was a problem in one of the earlier contests. And in that, there was, I think, a question at A rating, like the easiest question in the contest that used inclusion exclusion. But since I didn't know inclusion exclusion, I had to kind of invent this thing. In that question, we had 4 sets, A, B, C, and D, and I had to take union of those. And since I didn't know inclusion exclusion, I had to basically invent the thing on the spot. Yep. For 3, it is like visible. You can draw a graph and write a equation like this, looking at the graph. But the thing is, when there are 4 sets and you want to take their union and write a formula to calculate their union, it is hard. It is hard. It is very hard. And dearrangements, I guess that is inside inclusion exclusion. And then we have Burnside's lemma. Okay, and then Cayley's formula, yo. Okay, so that is going to be for today's stream. That is what we are going to go through. So that is cool. Combinatorics. Combinatorics studies methods for counting combinations of objects. Usually the goal is to find a way to count the combinations effectively without generating each combination separately. That makes sense. Usually the goal is to find the combinations effectively without generating each combination separately. Okay, that seems like a very good definition. Okay, if our problem concerns itself with counting something without going through every single possible thing that we are counting, then we can apply some combinatorics stuff and find the solution. Okay, as an example, consider the problem of counting the number of ways to represent an integer n as a sum of positive integers. For example, there are 8 representations for 4. Seems like coin change. A combinatorial problem can often be solved using a recursive function. In this problem, we can define a function fn that gives the number of representations for n. Yes, fn is defined as gives the number of representations for n. According to the above example, the values of function can be recursively calculated as this, and this is what we apply in coin change when we are finding the number of ways to get to a certain sum given some denomination of coins. The base case is 0. When we want to have a sum of 0, there is only one way to get to that sum, that is, do not have anything, because the empty sum represents the number 0. Then if n greater than 0, we consider all ways to choose the first number of the sum. If the first number is k, there are n minus k representations for the remaining part of the sum. Thus, we calculate the sum. So we vary k from, you could say, 1 to n. Yep. From, yep, 1 to n, 1 to n, 1 to n minus 1, 1 to n minus 1, or yeah, 1 to n, 1 to n, 1 to n, because k here is 1, and then we keep increasing k, and at one point we will have k equal to n, at which point we will get 0 representations for the remaining part of the sum. Thus, we calculate the sum of all values of the form fn minus 1, where k is less than n, is less than n. So we do not have to, yes, we do not have to go up to n. So we can skip this part, I guess. In that case, the first values for the functions are this. This is the sum of all the things behind it, and this is the sum of all the things behind it, and this is the sum of all the things behind it, and this is the sum of all the things behind it. This is somewhat like Fibonacci sequence, but instead of being the sum of the last two, this is the sum of everything behind it. Sometimes a recursive formula can be replaced with a closed form formula. That makes sense. That makes sense. Sometimes a recursive formula can be converted to a closed form formula. Okay, so we had this problem, and combinatorics gave us a recursive formula like this. And then we are saying that given a recursive formula, we can sometimes, not every time, sometimes convert that recursive formula into a closed form formula where you just apply the number that you want the answer for, and you will get the answer for that. Okay, but why does this one work here? I mean, we can verify that this formula works at all of these places, but why does it work? Which is based on the fact that there are n minus 1 positions for plus minus signs in the sum, and we can choose any subset of them. Okay, plus signs. Yes, they don't mean plus minus signs, they just mean plus signs. Sign. Okay, so that makes sense. That makes sense. That actually makes sense. If my target number is 4, then the basic representation is this. I have 4 minus 1, 3 places where I can put the plus sign, and I have with every plus sign an option to include this into my iteration or not. Let's say okay, 0 represents that I didn't include this sign, and 1 represents that I did. So let's actually go through all of them. 0 1 0 0 1 1, and then 1 0 0 1 0 1 1 1 0 1 1 1. So 0 means that we didn't include the above sign. So therefore, for this representation, we are having 4 because we didn't include the sign. So we had to add all the things, and then we are going to include this sign. So we can say plus 1 on the right, and on the left we didn't include any sign, so we would have 3. For this representation, we do include this sign, so this would be 2 plus 2, and then here we include this and this, but we don't include this, so we add these two. We will have 2 plus 1 plus 1, and then we include only this one and not these two. We will have 1 plus 3, and then we include this one and this one, but not this one. So 1 plus 2 plus 1, and then we include this and this, but not this one. So we'll have 1 plus 1 plus 2, and then at the end we include all the signs, and we will have 1 plus 1 plus 1 plus 1. And those are 8 different ways to get to a sum of 4 using using any of the positive integers when we are using plus sign. Okay, that is actually cool. Since I need to get to a sum of 4 or any, let's say n, I want to get to a sum of n, and it will have, if I want to represent that sum as sums of 1, then it will have n minus 1 places of where there will be plus signs. And with each plus sign, I have a choice either to include that into my final representation or not. So therefore, the number of ways is 2 power n minus 1. That makes sense. That is actually cool. Okay, so what have we done till now? That is actually cool. What have we done till now? Till now we have seen combinatorics is a study when we want to find the number of something, count of something, without necessarily going through every possible representation of the thing that we are counting. That is combinatorics. And yes, combinatorics can give us a recursive formula for finding our solution, and sometimes we can convert that recursive formula into a closed form formula sometimes. And now binomial coefficients, that is cool. Binomial coefficients. binomial co I have went through this in one of the earlier streams, but I wasn't at my best at that point, so we have to go through this again. Binomial coefficient, this thing. And okay, I can actually recall what we went through. When we have a equation of the form like this, a plus b power n, and when we expand this, we get something like 1 a power n plus, not necessarily 2, but some coefficient cn1 a power n minus 1 and b power 1. I think that is correct. And c power n to a n minus 2 b square plus dot 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 plus c n power n a power 0 and b power n. That is what we have. And since here we had two variables, a and b, well, 3, n is also a variable, but anyways, we had two variables raised to some power, binomial. These are, we call this binomial because there are only two things, a and b. So binomial. And the coefficient part, coefficient comes from the fact that this thing, this number is the coefficient to this binomial product. And yep, that is the thing. So NCR is also represented by N choose R, and we call this binomial coefficient because this is the coefficient that we get when we do a binomial expansion. And binomial simply means that we have two variables, a and b, and its coefficient we call it binomial coefficient. So that makes sense. Binomial coefficient, and choose k equals the number of ways we can choose a subset of k elements from a set of n elements. For example, this, because of the set, because the set this has 10 subsets, each of element 3, which is this. Binomial coefficients can be recursively calculated as follows. Okay, so before getting to the formula for calculating this thing, I want to ask ChatGPT a few questions. This is one of those things where two seemingly unrelated concepts connect in mathematics. So in mathematics, there are times when two seemingly unrelated concepts seem to connect in some way, and the underlying formulas and the numbers involved might be the same, but but the mental model with or mental model but the mental and mathematical model they are a part of might be different, and that is the case with binomial coefficients. We have equations or expressions of the form a plus b raised to the power n, where there is a way to find the coefficients coefficients of a to some power and b to some power, and we call them binomial coefficients. And this same formula applies to choosing some elements given a set of elements and two other places also. But before this, I just thought of something. This thing, what does this essentially even mean? This means that I have a plus b into a plus b into a plus b into a plus b, and this goes on n times. So for every representation here, from let's go small. Let's go small. When we have AB into AB, when we have this, from the first one, we have the option of choosing A or choosing B, and then again A or B. Let's say we choose A from both the things. Is that the right thing? Okay, we choose A from both the things, you will have A square. Then we chose B from both the things. Let's say we will have B square. When we choose A from the first one and B from the second one, we will have A B, and then we chose B from the first one and A from the second one, we will have B A. And now we have A square plus B square plus 2AB, which is correct, which is correct. So how do we get a coefficient of 2 here? A square plus 2AB plus B square. Why do we have a coefficient of 2 here? Why does this work? Okay, what is this thing essentially? What does this mean? This means that given, let's say we have steps. Okay, in the first step I can choose A or B. In the second step I can choose A or B, and also in the I have in total n steps, and at every step I have option of choosing A or choosing B. So what we are asking here, this coefficient is going to be equal to the number of different ways in which I can choose this particular thing. And okay, let's say I have n choices. In total I have n choices, that is the thing. And from that, okay, in total, since I have n choices, and let's say I choose k number of b's, k number of b's would give me b power k. And since the places where I didn't make a choice of choosing b, I must have chosen a, so I will get a power n minus k, n minus k. And how many ways? So this is basically the same thing. This is basically the same thing. So how many ways can I choose k number of b's out of n? We represent that like this, which is binomial coefficient. So that is cool. That is cool. That is cool. That is cool. Yes, but there is a little difference. There is a little difference. Yep, there is a little difference. Let's say we have a lot of boxes or something, a lot of elements, let's say n elements, and choosing an element means we are counting that as B. So that is the thing. Hmm. That is the mental model. That is the equivalence. Makes sense. That is why this thing works. That is why this thing works, because there are two extremes. For a plus b power n, at one extreme I will have a power n and b power 0, and at the other extreme I would have chosen all the b's from all the n choices, and I would have e power 0 and b power n. Now the question is, how many ways is this thing possible, and how many ways are there in which this thing is possible, and how many ways are there for everything in between? And their powers has have to sum up to n, because there are always n choices. At every bracket position, we could either choose a or a B. And now, since we could represent choosing a bracket as the number of B's that we choose, in which case we will have like this. Let's say we chose k number of B's, so we would have our equation like this: a power n minus k b power k. That is cool. That makes sense actually. That actually makes sense. And in this set representation, in this, when we have 5 elements in a set and we want to make 3 choices, when we have 5 elements in total in a set and we want to make 3 choices, we write it as this. And now we have formulas for this. Let's see, there is a recursive formula. Okay, I will not look at the formula. Can we like actually derive the formula? I have only read this part, that there is a recursive formula. So let's try to formulate. Let's try to actually formulate what it could be look like. Okay, let's go with a general case, or starting small is pretty good. Let's say I have 3 total elements and I want to choose one element from that. So what can we say? Let's say, since I have 3 total choices and one, let's say I make one choice and choices cannot repeat. So let's say I make one choice and I had 3 choices. So 3 multiplied by, since I made one choice, I have already made one choice, I have 2 choices remaining, and from that I have to make 0 choices. So here the answer is 3 into, how many ways are there to choose 0 things from 2 things? It is simply is 1. That is just, I don't choose anything. So okay, that makes actually sense. Okay, if I want to make k choices from n elements, let's say equal to, let's say I made one choice from this k, so I would have n minus 1 choices remaining, and I have to make now k minus 1 choices, and this just keeps on going at one point. Okay, yep, multiply this thing multiplied by n minus 1 and then multiplied by n minus 2, and this will keep on going at some point where we will have n minus k divided by, not divided by, choose 0, and the value for this thing, this is our base case, value for this thing is 1. So we would have n into n minus 1 into n minus 2 into dot 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 till n minus k, which actually is the formula. Is this the correct thing? Okay, this is a bit different. We are doing some addition here. This part is the same, but we are not adding. We are not multiplying this by anything. We are adding some other number. Okay, I think this just means we start from the starting element, and let's say we made a choice. We are reducing our sample space from which we can make a choice. And yes, we are reducing our sample space from where we can make a choice. N, K, this is what we began with. And then we had N minus K choices, numbers left from which we could make a choice. And let's say we did make a choice, therefore we would have, if we chose this current number, then we would have K minus 1 choices, plus if we didn't choose the current number, we would have k choices remaining. And if we expand this further, we would reduce our choice space again by 2 by 1. And if we did choose the current element, we would have k minus 2 choices remaining for this part. And if we didn't, then we would have still k minus 1 choices remaining, plus n minus 2 for this, and we did make a choice, so k minus 1 plus n minus 2 into k into k. And this term is going to end when we are choosing n minus something and we have n above and n below. Answer for this thing would be 1 at the end, and these two are the same, so this would also terminate at some point, and this thing would end when we have n minus k choose 0, which is also 1. These are the middle terms which are expanding, and this becomes n minus 2 k minus 1 into 2, because these two are the same. And we just expand these, and yeah, recursive formula. And we can say that this is going to work because whenever we expand our formula, we are making sure that these two things are equal. Right? When we wrote this thing as the sum of these two things, we know for a fact we made sure that these two sum equals this original thing, and then at every step we are making that sure. And we also have defined some base cases so that at some point we would have some integer value to work with. And yeah, so this should work recursively. By induction we have proved that this formula is correct, so that is cool. The idea is to fix an element x in the set. If x is included in the subset, we have to choose k minus 1 elements from the n minus 1 elements. And if x is not included in the subset, we have to choose k elements from n minus 1 elements. And the base cases are this: the thing at the bottom becomes 0, that is 1, and the thing above and below become same, that is also 1, which is also our base case. When we have 0 at the bottom, it is 1, and when we have both the things equal to the same number, then also it is 1, because there is always exactly one way to construct an empty subset and exactly one way to choose n elements from given n elements. So that is cool. Hello. Yep, we are doing some combinatorics. We are trying to do some combinatorics because combinatorics is like not really tough, but yeah, it helps a lot because we have done 1400 rated questions till now in CP31. Yep, all of these questions. Now we want to break into doing 1500, and I think including combinatorics and also some other things like probability, I guess, would help us, and graphs and trees would help us when we go to 1500. So we are studying, improving ourselves. And this is something I was asking ChatGPT. That is cool. To be used for, where did you find that book? Okay, someone suggested this book in very one of the earlier streams. I guess it was only second or third stream on competitive programming. Someone suggested this book, and you can also go and read this book. This is online available for free. Competitive Programmers Handbook. That is cool. What is this supposed to be used for exactly? Well, there is the mathematical definition for binomial coefficients, right? This just means the number of ways to choose k things given a total of n things. And this can be related to a lot of things that you do in competitive programming. I have, I think I have only been able to use this a few times. Yes, yes. There was question. There was a question. There was a question in which I had an array of elements A, B, C, D, and some things. There were total n elements, and it was that there were some elements, some choices of elements. Let's say k elements. K is lower than or equal to n, which I had to put at each ends. So I had to rearrange the array and put these chosen k elements at either ends. So if here B is one of the chosen elements and D is also one of the chosen elements, and let's say we also have E, then I could make this that B comes at this end and D comes at this end. Then there is also D comes here and B comes here. Then there is also, well, this is permutation. We do not count this. And then there is B and E and D and E. So here, given k number of total elements, we had to choose two elements, which is going to be equal to k into k minus 1 if we apply the formula. So yeah, it does come handy. So that is cool. Yep, it is the CACS one. Real world example, how would you apply this or use this in a real world? Yeah, it helped me in a question. So that is cool. And I'm not a very good mathematician. And I think I cannot think of any example at the top of my head, only apart from this one, where I used this. Or maybe you can think of you have k friends and you can only have enough money to give party to 3 friends, and therefore you would have k choose 3 combinations of those friends to consider from. That is also one thing. But yeah, this does help. This does help. And we have Formula 1, which is recursive. And we can move on to Formula 2. But this definition of combinatorics that they have given here is pretty cool. Combinatorics is used to count the number of ways for representing something or number of ways of something without necessarily generating each combination separately. So we want to count something, but we do not want to generate each single combination that we are going to count. And those places we apply combinatorics. That is cool. And often we can create a recursive formula for finding our solution, or sometimes we can convert our recursive formula into a closed form formula where we just apply, put our number and get our answer. And here also we have this recursive formula. And now we can move on to formula number 2. What do we have here? Another way to calculate binomial coefficients is as follows. Wait, so this was wrong then. This was wrong, I guess. Yep, I messed up here. This is for permutation. That is why I have to work on combinatorics. There are, okay, we did in one of the earlier streams, we did some chat GPT research in which we found out why this thing works. We found out why n choose k equals n factorial divided by k factorial into n minus k factorial, and it was pretty cool. Let me show you. All right. So also the stream is a bit laggy in a way that it pauses for a few seconds and maybe sometimes on my end. Shit, it is. And okay, It says on my OBS that 0 frames have been dropped. So maybe it is something on your end, and do not say bad things like that on the stream. Okay, so why does this formula work? When we want to find the number of permutations given n elements and we want to find their permutations, it is going to be equal to n factorial. Why? Because I have n possible things. I have n possible places, and to put on in those places I have n elements. So at the first place I have n choices, and since I have made my choice on the first place, for the second place I have n minus 1 choices, and then for the third place I have n minus 2 choices, and for the fourth place we have n minus 3 choices, and this goes on till at the last place we only have one choice, the only remaining element. And what this gives us, the formula would be n into n minus 1 into n minus 2. This goes on till into 1, which is n factorial. So that works, right? That is the formula for factorial. But we do not want to choose n things. We only want to choose k things. So we can say, let's say when n equals 3, let's say we have 3 elements, 1, 2, and 3. And if I were to write down all the permutations, 1, 2, 3, 1, 3, 2, or 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. These are all the 8 permutations for these 3 numbers, comma, comma. And let's say we want to choose k equals 2, two things, just two things. So if we just take the first two things from these, we will have these as our like choices, but we have repetitions here. Here we have 2 1 and here we have 1 2. We do not want to count them as separate. We want to count them as the same thing. And also we have 2 3 and 3 2, and we have 3 1 and 1 3. We do not want to count them as different things. So let's not just say, but actually do. We have a repetition of 1 2 and 2 3, and we do not want to count them as different things. We want to count them as the same thing. And what this essentially is, it is just permutation for two numbers, number of ways to represent two numbers in a permutation. Just mumble them up here and there. So if I divide this thing by the number of ways to represent two elements in different permutations, that would be 2 factorial, since there are two things, 1 2, and I would get 1. And I can do this with all the elements here. And since in all the elements here we have two elements, two numbers in everyone, in all the elements, so in total we have n factorial things, and among those n factorial we have k factorial repetitions. So we divide n factorial divided by k factorial to get unique things from here. That makes sense. But here also we have some things remaining here. Let's say there was also a new element, a different element, 0. If there was 1, then here we have for something like this, 1 2 and 2 1, we have divided this by k factorial to count these two as a single thing. But here 3 0 and 3 0, this could also have appeared in different combination. Let's say 1 2 3 0 and 1 2 0 3. So these things that we didn't count could also have different permutations. So we have to divide this thing again by n minus k factorial, because when we choose k things from n things, we had n minus k things remaining here, and these things could have their own internal permutations, but we do not want to count their permutations. We want to count them as a singular thing. So this is the formula. In total, we have n permutations. We divide that by k permutations and n minus k permutations. I guess that makes sense. How about some background? What you do? I am in college. I do not go to college. I'm in my third year, but yeah, I'm in college. College near my house. So yes, we have in total n elements, and like this, and we want to choose k elements, k, and when we chose k elements, we had n minus k elements remaining, and we have in total k permutations for rearranging this whole thing, and we have k factorial permutations for rearranging this little part, and then we have for rearranging this part, this remaining part, n minus k permutations. And I hope that makes sense somehow. Yep. And this is like, when you do understand this thing, this seems very elegant, and this formula suddenly starts making a lot of sense. Just somehow it does make a lot of sense. This thing, and this is essentially what this is. There are n permutations of n elements. We go through all permutations and always include the first k elements of the permutation in the subset. Since the order of the elements in the subset and outside the subset does not matter, the result is divided by k factorial and n minus k factorial, and this exclamation mark makes it feel even more dramatic somehow. So we have total k things. There is some internal order for k things, and the k things that we did include our subset, and the remaining n minus k things, their order does not matter, so we divide them by their number of permutations that we can choose them. Plan set job. Yep. Right now I am learning getting better at competitive programming, and that is the main goal for this year. I want to get really good at competitive programming, and once I've done that, I think I will become a better programmer in general, and just keep keep taking it up from there, keep improving. Yep. I want to become really good at these things. Yep. And through streaming, since I'm not just thinking, I'm also explaining my not vocabulary exactly, but my articulation is improving. I cannot spell. My articulation is improving, so that is one of the very good plus points. Yep. Thank you. Yeah. Properties. What are the properties for binomial coefficients? This thing. Huh? Yes, that makes sense. That makes sense. Like, if I do n k, which is going to be equal to n factorial divided by k factorial into n minus k factorial, and if I do n minus k, it is going to be equal to n factorial divided by n minus k factorial, and you could write it as n minus plus k factorial, which is essentially just n factorial divided by n minus k factorial into k factorial, which is the same as this thing. So these two are similar, and not just in formula sense, but also in this analogy or this framework of looking at this thing. If we are not choosing this as our subset, if we are not choosing this part as our subset, but instead we are choosing this part as our subset, our problem like is actually the same thing, like it does not matter, right? It would result in the same formula. So they are equal because we actually divide a set of n elements into two subsets, the first containing k elements and the second containing n minus k elements. The sum of binomial coefficients is 2 power n. Now that is interesting. The reason for the name binomial coefficient can be seen when the binomial this is raised to the power to the nth power. So the things that we have in the coefficient are the coefficients, and since they have been, they are the things that we gain when we have a binomial raised to some power, and these are the coefficients of that binomial expression. These are called binomial coefficients. That's cool. But why is this? That is strange. That is strange. Yo, thank you. I assume you are in it. Yep, by the name, and yep, just good to guy improve. Yes, thank you. No, I do not think AI is going to take my job. If I am really, really good, then AI cannot take my job. If I'm really, really good, that is the big if. But yeah, it won't be able to take my job. If I'm really, really good, to emphasize again on the real if. And why is this correct? Why does this thing work? And also, apart from me improving, the main thing that I feel is lacking or is bad in Indian culture is that when we think of studying, it is the mindset with which we think of studying is very bad. Is very bad. It is just study because you want to get good marks in school, or yeah, study because you want to get a job, study about different things because you want to get something else, but we are not studying for the sake of studying. And I think maybe if some more people start to watch my streams, then I can show these things are fun. These things are like actually fun. Mathematics is fun if you think about it in that way. So you do not have to think about this in a limited way as a means of getting someplace else, but you can study for the sake of studying. You can study physics, mathematics, anything for the sake of studying, just because you like them, not because you want something else, right? Studying is fun. Being curious and getting to know how things work, that is very, very fun. And okay, I'm not at a place to lecture, but yeah, it is very, very fun. It is very, very fun. True, yes. Binomial. Yep. Thank you. Do not call me sir. I'm just like, I'm no different than anyone else. A plus b power n b binomial expansion. Shit. That is shit. Okay. A plus b power n. And if we do a equals to 1 and b equals to 1, we have 1 plus 1 power n, which is 2 power n. Okay. Okay. But why is this? Shit. Okay. 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 This does make sense. This does make sense because if we expand this into the generic equation like this, C or yeah, let's use C, n C0 and a power 0, b power n plus n C1, a power 1, b power n minus 1 and dot 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 till the end where we will have n C n a power n and b power 0. If a and b equal to 1, then their power does not matter. We can just cut them off, right? And what we have essentially is C nc0 plus nc1 dot 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 plus till ncn, which is going to be equal to power n, like here. So that is cool. That is very cool. That shit. These are like some of those things when you just have a little insight, change the formula a little bit, and you see the whole thing. Yeah, getting us. And there is one more thing about like this. There is a question. Let's say there is a game of like badminton or something else. Let's say badminton, and you have two players, player A and player B, who are competing with each other. They are playing the game, and in each game, let's say there are sets. There are sets. Let's say in total there are three sets, and in each set, the player who scores 3 points first wins. Let's say in the first set we had A point score a point, then B, and then A scored 2 more points. Then A won this set, and then in the second set we had, let's say, B score a point, then A scored 2 points, and then B scored 2 points, then B won this set. And in the last set, let's say A scored all the points, then A won that set. So in total, we have A winning the whole thing. A won the whole match, and in each match, we had a number of sets, and in each set, we had points. And if someone gives you this string A, A, B, this whole thing, B, A, A, and you have just this, and you know the number of sets that there were and the number of points required in each set to win that set. How would you find who won the whole game, A or B, if this is all you have been given? And there is a very simple thing which you can apply here to find which player won the game. And that thing is, you just see who scored the last point. That person won the whole match. This whole thing does not matter. The person who scored the last point won the match. Because first, let's apply this to the set. The individual set for a person to win a set. And yes, I gave it away. I think I like told the answer very fast. I should have given you a little time to think. Can we, if we try to obtain the sum, okay, Titan, similar thing can be observed if we try to obtain the sum n using numbers from 1 to n, we will have 2 power n minus 1 possible ways to do so. Yes, yes, yes. Yes, it was like right here. Mm, so, yep, this thing, 2 power n, because we can represent n as sum of ones and with plus signs in the middle, and for every plus sign we have a choice to either include that or not in our thing. And since we have total n number of ones, sum up to get to n, we will have n minus 1 plus signs, and for every plus sign we have a choice either to add it, either to have it in our final expression or not. So in total we will have 2 power n minus 1 possible ways to represent that thing, the same thing that you said. And getting back to this thing, why does this work? Why can we just look at the last thing and see this is the guy who won the whole thing? This thing does not matter, because in individual set, for a player A or B to win the set or win the set, or even these individual rules that there are this many number of sets, or there are in each set you have to point 3, 5 or 7 number of points, it does not matter, because in each set, whatever is the rule, you must win odd number of points, something 1 plus n, where n is even, or you could say 2n plus 1, 2n plus 1 number of points. And at max, if A wins the match, then the last point, if A wins this set, this particular set that we are talking about, if A wins that, then A must have scored the last point, because how is it possible in the other way? How is it B scored the last point and it was A who won the match? This is not possible, right? Because if A had already scored enough points to win the match, why, to win this set, why they were playing it, why were they still playing, right? So if A at any point scores enough points to win the set, A wins the set. So the last point was scored by A, and same for B. If B wins a set, then the last point must have been scored by B, and we can apply the same logic in the total number of sets. If we have 3 sets and if let's say A wins the whole round, the whole match, then let's prove by contradiction. Prove by contradiction. Okay. The claim is that if A won the whole round, the whole match, then A must have scored, must have won the last set. And why is that true? Because let's prove by contradiction. Let's say B was the one who won the last set. And if B was the one who won, WON, won the last match, the last set, then, and we are saying that A is the one who won the whole match, then this last set was of no consequence. If A had already scored enough points, if A had already won enough sets to win the whole match, we wouldn't have this extra set. Why would we have this, right? So the match ends when A wins or either B wins. So that is why whoever scored the last point is the one who won the set and the whole match. So that is cool. That is actually pretty cool. A single simple observation to skip through the whole simulation thing. That is cool. And now we know this, why this thing works, because thanks to Indresh Chaun. Yep. And now this, yep, we have discussed this also in the start at the start of the stream. Now Pascal's triangle. Why are they important? I do not know why they are important. I was watching some combinatorics videos and there was a person who was like talking about combinatorics, and she kept saying that if anything is about combinatorics, then Pascal's numbers are there. Pascal's triangle is there somewhere. I don't know why that works, but that works somehow. And yes, when we get to Catalan numbers later, when we get to Catalan numbers, I will show you the way that she showed in the video how Catalan numbers can be derived from Pascal's triangle. Before that, why is Pascal's triangle such a thing? Why is Pascal's triangle important? Like, why do we need it? Pascal, the pronunciation that we are going to go with is Pascal is the one. Okay. Pascal's triangle is deceptively simple, just a triangular arrangement of numbers, but it is one of the most important objects in mathematics. Okay, because it secretly encodes an enormous amount of structure. Uh, Okay, because it secretly encodes an enormous amount of structure. Let's break down why it matters. Okay, combinatorics, yes. Combinatorics, yes. I mean, not yes in the sense why, but yes, it is in combinatorics. Each row gives you the coefficients for expanding row. Shit, shit. Okay. Shit. Pascal's triangle 1, 1, 2, 1, some 3, 3, 1, and 1, 4, 6, 4, 1. And the claim is if I have A, yes, this the claim is this thing. What is the claim? Power. Yes, A plus B power 1. Yes, yes, I think that is correct. A plus B power 2, A plus B power 3. Let's go with these three for now. For here, we have just A plus B and the coefficient for both is 1, right? Since we have infinite number of ones at every place, so 1, yes. And then we have A square whose coefficient is 1. Then we have into 2 to AB plus coefficient 1, 1 into B square. That is cool. And then for 3, we have 1 as coefficient of A cube plus 3 AB square. Then we have 3B A square. And then we have 1 again as the coefficient. I think my writing is not very good. Like that is the best I can write with a mouse. 3B cube, 1 into B cube. That is cool. And somehow these things work when you will see how we can derive Catalan numbers from Pascal's triangle. From Pascal's triangle, it just does not make sense. How is it even, how these two things are even related? And this thing, how is this related? How how does this work? Why does this thing equals this thing? Why is this even working? Each row gives you the coefficients of for expanding this. Okay, this is huge. Yes, this is huge. Combinatorics choosing k things from n things. N k comes straight from the triangle. Yes, but why? Probability. Binomial probabilities use these coefficients all the time. Think coin flips. Coin. Okay, we will talk about probability when we get to probability, but I think we can do something. Yes. Okay. This does not make sense. Does why this thing works? Why do numbers, rows in Pascal's triangle give us the coefficients in these things when we expand these binomial expansions? Why? A cube, A B square, A square B, B cube, It is correct, but why? Does not make sense. OBS is fine. It says his stream is going fine. Okay, we can get to boxes and balls, but let's read the whole thing. Hidden patterns everywhere. Pascal's triangle is like a math playground. It contains triangular numbers, sum of natural numbers. Okay, what are triangular numbers? I've heard about triangular numbers, but I don't know. I will have to look that up. We know about Fibonacci numbers, so that's cool. Add along diagonals. Fibonacci sequence is 1, 1, 2, 3, 5. 1, 1, 2, 3, 5. So we have 1, we have 1, we have 2, we have 3, and here we will have 5 because 4 and this. So why did we skip 4? Did I mess up? No, this is the Fibonacci number, Fibonacci sequence. For 5, then here we would have 10, and here we would have 15, 1, we would have here 6, and if we go below, we have here 1, and then we will have 7. This is just increasing by 1. So that is not the right thing. Okay, so we have Fibonacci numbers. Add along diagonals. Where do we have Fibonacci numbers in Pascal's triangle? 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 6, 15, 20, 15, 1, 6, 1, 7, 21, 35, 35, 21, 1 and 7. And the first Fibonacci numbers are 1, 1, 2, 3, 5, 8, and where are they? Where are they? We have 1, we have 2, 3, 3, 5, 5. We don't even have 8. 8 will be here. But this is not Fibonacci. I mean, the numbers on the diagonals are always increasing by 1. So you could say you will have all the possible integral series here on the diagonal. So that is not very interesting. If that is where the Fibonacci numbers are. Powers of 2, sum of each row. Check. Okay, this powers of 2, the sums of each row. The sum of this thing is 4. The sum of this thing is 8, which is correct. Sum of this thing is 8, this whole row. Sum of this whole row is 16. Yes, 16. It is 16. Sum of this whole row is 32, which is correct. And this just follows from the fact when we put a 1 plus 1 power n. Yeah, right. That is just 2 power n. This follows from there. So we will have to see why Pascal's triangle has binomial numbers, has binomial coefficients in them. Sierpinski. triangle, fractal. Look at odd even numbers. What? Okay, look at odd even numbers. I will have something. What do I look at? This is even. This is even. Okay. Wait, why are all the numbers on this row odd? Hmm, that is interesting. Here we have even, even, even. Here we have even, even, and odd, odd. So odd would always be there because we always have one. Here, everything is even. Everything is odd. That is interesting. Mhm. That is something. Foundation for algebra and discrete mathematics. Practical uses, gateway to deeper mathematics, combinatorics, number theory, abstract algebra, mathematical proof techniques. Okay, that is a lot. We cannot do everything. So we will see why do we have binomial coefficients in Pascal's triangle. And ChatGPT is one of the best things, like literally one of the best things. I can ask everything particularly that I want to ask. I think triangular numbers are like 3, 4, 5, where like shit, like Pythagoras theorem numbers, triangular numbers. Triangular numbers are figure-8 numbers represented as an equilateral triangle of dots where each row has one more dot than the previous. They are formed by summing consecutive natural numbers, etc. Okay, and follow the formula this. Huh? Sum of the natural numbers. 3 figure-8 numbers represented as an equilateral triangle of dots. Okay, okay. Triangular numbers. Where triangular numbers is a series where we have a bunch of numbers. The first triangular number is 1. The second is when we create a new triangle, but we apply where every side has 2 balls. So in total we have 3. So we are considering 3 as a triangular number. And if we increase the size of each row from 2 to 3, we have 1, 2, 3, 1, 2, 3. Now we have 6 balls. 6 is a triangular number. If we have 4, if we increase the side to 4, yep, here the sides are 4 and the drawing is absolutely amazing. The sum is 10. So 10 is a triangular number. And since we had 1, we can look at this like this. We added a layer of 2 balls. So we added 1. We had 1. We added 2 to it. And then we added 3. We added a layer of 3 balls. And then in here, we added a layer of 4 balls. 3, 4 plus 4, which is 10. So which is just n into n plus 1 by 2, which is 1 plus 2 plus dot 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 till plus n. These are triangular numbers. Okay, that I don't know, that makes sense. But why a triangular? They are called triangular, I guess, in the sense that we can make equilateral triangles. Not that we can make equilateral triangles, but we get them from making equilateral triangles. Okay. Gateway to deeper mathematics. Okay. Now, I only. Why is my typing slow? Want to know one thing. Why does Pascal's triangle have in them somehow? Triangle has in it somehow the binomial coefficients which we get from the binomial formula, of course. Binomial coefficients. Why does it have them? That is the heart of it. Pascal's triangle gives the binomial coefficients because of how the triangle is built and how binomial coefficients behave. And I can say, like before getting into this, that we might not be able to understand why we have binomial coefficients here. We might not be able to understand it, but we can try. Let's be precise. Definition of a binomial coefficient. This thing. This is the formula, but okay. This counts the number of ways to choose k things from n things. Okay. But it also satisfies a recurrence relation. It does. It does. It does. It does. And when we write binomial coefficient, and when we write Pascal's triangle, it is also a recurrence formula because it depends on the two things later. And so any number in Pascal's triangle depends on two things, to its top, one on the left and one on the right, and we sum them and we get this number. And if we somehow can relate this and this with the things on the left and on the right, we have proved our what equivalence, I guess equivalence in binomial coefficients and Pascal's triangle. Okay, so can we, so we know n k equals not arrow equals n minus 1 k plus n minus 1 k minus 1. We know that. And let's start from the beginning, from Big Bang. No, let's write Pascal's triangle. 1 1, yes, 1 1, and then we have 2 1 1. Okay, we have to represent this in some better way. This number is equal to 2 1 when we have two choices and we are only choosing one number. This number is equal to that. And we have, if we apply this formula, above formula here, we will have 1 1 plus 1 0. And we are saying this thing equals 1 1 or 1 0, does not matter, both are equal to 1. And this, okay, okay, and then in the next layer we will have 1 3 3 1. And okay, and if we write, when we have three choices, so when we go down a layer, our number of choices increases. Here we had two choices, here we will have n equals three choices, and this number represents when we have chosen out of 0 things. Here when we have chosen 1 things, here when we have chosen 2 things, and here when we have chosen 3 things. So in general, that actually makes sense because this thing is going to be the sum of these two. So here in like particular, yeah, we have 3, choose 2, not 3. 3 choose 2 is the sum of 2 choose 2 and 2 choose 1. And since the number of choices was 3 here, and it is reduced to 2 in both the cases. In both the cases, it is reduced to 2. So what this means is, from this layer, we went to the above layer to find the solution for this thing. And so we have to relate these two things by this two. So we can say here 1, 2, 2, or we don't even have to write this. Here this is the first element, here this is the first element, this is the second element. In the third layer, we have this as the first element, this is the second element, this is the third element. Here we have this is the first element, this is the second element, and I am not creating Pascal's triangle. I am representing the this second number in Pascal's triangle. This is the fourth element, this is the first element, this is the second element. Here 4, 3, 4, and 5. So when we do our formula, let's say we are at some nth layer, and we have 4 here, or any number k. We can from this see that, let's say this is k. Above k, on the right of k, we have k, and on the left of k, we have k minus 1. And in the triangle, we defined this number as the sum of these two. And this, we are not adding k minus 1 and k. We are adding what the k minus 1th number is on the above layer and the kth number on the layer above. That is what we are doing. So we write this thing as n minus 1 k plus n minus 1 k minus 1. And here this n minus 1 means that we are going to the layer that is above our current layer. Our current layer is nth layer, and n minus 1 layer is the above layer, because here we have 6 choices. No, here we have 5 choices. Here we have 4 choices, 3 choices, 2 choices in total, and 1 choice in total. That is what the layer represents. And this k here is represented by, in that layer, which number is this? In that layer, which number is this? Right? It represents how many choices are we making from the available choices. So all of that, and from our recurrence, we can see, first of all, we are going to the layer above, to the above layer by this n minus 1. We can see that, and then the number here below, we are adding whatever the value is at the kth position in the above layer, and the value at the k minus 1th position in the above layer. That is how we define Pascal's triangle also. We are adding the number at the k minus 1th layer and the number at the kth layer, and we get k, the number at the kth position, which is correct, which is also how we define the recurrence in Pascal's in binomial coefficient. There is equivalence. There is a specific word that we can use. There is a specific word which we can use here, which is like the equivalence. In mathematics, sometimes there are concepts which are derived from different mathematical concepts, but and we and might just share some similarity and might just share some similarity and thus same and thus uh, one can be represented as other the other, that is these two models can be interchanged interchanged without any logical loss. And there is a specific word for this phenomena. Uh, what is it? Sometimes have a look at number file and 3 blue 1 brown for search patterns. Yes, number file and 3 blue 1 brown are pretty cool. I watched the Catalan video on number files. It was by I remember the name of the person. Ah, Sophie McLean. Sophie McLean. Yeah, Sophie McLean. Catalan numbers. And on 3 blue 1 brown, a video that I really liked was a video in which he explains math Olympiad IMO problem question in which was like very hard because only a few people were able to solve it. But the thing is, I was able to understand the solution to that thing, which is crazy. It had something to do, the specific question had something to do that in a 2D plane, we have a bunch of points and these points are non-collinear. That is, no 3 points lie on the same line. That is given. And you start with a line between any two arbitrary points and this line is moving in some rotational direction, and whenever this line touches another point, it goes to that point and uses that point as the pivot and starts rotating from that point, and whenever it touches any other point, it makes that new point as the pivot and starts rotating from that point. And you had to prove, is there a way, given an arbitrary set of these points which are non-collinear on a 2D plane, can you find placement of this line on such a point such that it will touch all the given points at least once or infinite number of times? And yeah, the solution in the video was very elegant, pretty elegant. And the term turns out to be essentially the same, so you can switch between them with no loss of information. The word you are looking for is isomorphism. Isomorphism is the word. Isomorphism, the precise term. Isomorphism is not the precise term there, but what does isomorphism mean precisely? Iso, same, morph, form. Isomorph, same form in mathematics. An isomorphism is a mapping between two structures that preserves all the relevant operations and relationships. Okay, if two structures are isomorphic, they are structurally identical, just presented differently. So I can find myself using this term a lot more from now on. Example, integers mod 2 under addition. Integers mod equals Boolean algebra under XOR in different concepts and same structure. Yes, we have already seen the isomorphism between Pascal's triangle and binomial coefficient. Different construction, same recurrence. Yes, same recurrence. So isomorphic as combinatorial objects. Okay, Okay, that is isomorphism. But what is this isomorphism? Boolean algebra under XOR and modulus 2. Okay. Uh, okay. They are, I guess, saying if we create a table of XOR, and these are the possible things for XOR 0, 1, 1, 0, 1, 1, we get 0, 1, 1, 0, right? And if we do the same thing in modular terms, if we have like if we go like this and we have two numbers, one number is that has a remainder of 0 with 2 and the other also has a remainder of 0 with 2, and if we add those numbers and then take a remainder of that new summation number with 2, we will get 0, which is correct, which also makes sense. And if we have one number here which gives a remainder of 2 when divided by 2, and which gives a remainder of 0 when divided by 2, and another number which gives a remainder of 1 when divided by 2, and if we add those two, the resulting number is said to have a remainder of 1, which is correct and which is also equal to the XOR of 0 and 1. And if we go like interchange the numbers, still we will get 1. But if we have both the numbers here at the 1 position, that is both of them give a remainder of 1 when divided by 2, which means both of those numbers are of this form, 2n plus 1 and 2m plus 1. That is both the numbers are odd. If we add them, we will have 2 into n plus m plus 1, which is even and will give us a remainder of 0, which is also equal to the XOR of 1. When both the numbers are 1, we will get a XOR of 0. So that is isomorphism. Shit, I will be using this term a lot more. Okay, isomorphism. Other possible words, but less precise. Equivalence, yes, that is what I was using till now. Duality, shit, yes, I think duality is the word, is the thing I was looking for. Duality, duality. Wave particle duality. Yes. Duality. Equivalence. Loser as in like lose, not as in like defeating lose, but lose as in tight and loose. A loser term used when two things are the same for all practical purposes, but maybe not literally identical structure. Correspondence, that is also a nice word. Duality, when two different frameworks describe the same phenomena, but from opposite perspective, common in physics and category theory. Okay, category theory, we have category theory. But the formal mathematical term for what you described, interchangeable model with no logical loss, is isomorphism. Okay, here they are saying that duality is used for two different frameworks which describe the same phenomena. But I thought we have a phenomena which can be described in two different verb terms, frameworks, which is the same thing, Okay, isomorphism. Isomorphism is the term that we were looking for, and we can move on. Pascal's triangle. I guess, cool. Pascal's triangle has a lot of structure in it, which can be related in isomorphic terms with other things like binomial coefficients. That is what we got from ChatGPT. And now we can move to boxes and balls. Boxes and balls is a useful model where we count the number of ways to place k balls in n boxes. Let us consider k balls in n boxes. There are three scenarios. Scenario 1, each ball can contain at most one box. So, which is just the binomial coefficient. Yeah, 5 choose k. There are 10 solutions. If this is our scenario, one box can contain 2 balls, then the answer would be 5 choose 2, which is 5 factorial divided by 2 factorial into 3 factorial, and if we cut 3 we will get here 5 and 4, 4, 2, 10. 10, this is not 1u, this is 10, and we do get 10, so that is cool. In this scenario, the answer is directly binomial coefficient. That's cool. Scenario 2, a box can contain multiple boxes, for example, multiple balls, multiple balls, multiple balls, multiple balls. Okay. Do you know he created the library to animate? Yep, yep, in Python. And there is a community version of that library which we can just use. It is open source. And he personally recommended that the community version of his library is much more maintained. And if you are going to use something like that, then you can, instead of using his personal library, it would be better to use the community version. And I think it is like so cool. He said he started working on his library when he was in college, which is cool. One more fact, his channel name is based on his right eye. You know, his right eye is of different color. 1/4 of his right eye is brown and the rest is blue. Shit, I never noticed. Huh, shit. His name is Grant, I guess, or something like that. One eye color. It is hard to see, but huh, that makes sense. It looks more green, but yeah, cool. It is hard to see in the videos. Like, how do we see 1/4 of his pupil? But not pupil. Pupil is a little thing. So that is someone else. But cool. Shit, maybe this is not even him. This might be someone else. I don't know. Deleted person posted this. Okay, so this is not him. This is someone else. Okay, but yeah, that is cool. That his eye is in this strange pattern. And to this question, now we can place any number of balls in boxes. So when we have boxes, let's say 4 boxes and 2 balls or 3 balls at start, let's say we can only place 1 ball in a box. That would give us n choose k number of ways to do that. And let's say now we will pick one of those balls up and put it in at some other place, right? And now, yes, we picked one of the balls up. Yes, we didn't put it anywhere else. We just picked it up. We have the third ball here, and now we have 2 balls, and which is k minus 1 balls, and n boxes. So this many ways to put them. And now since I have 1 ball, and this ball can at any given time go into k minus 1 boxes. Yep. So if I have my first ball here and my second ball here, this third ball can go here or go here. And if we had a third ball and we had 1/4 floating ball, it could have gone here. So in total, we have k minus 1 ways to place this ball, and to place these 3 balls among n boxes, we have n into k minus 1 ways. So I think we can multiply this by this. That is cool. That is cool. And when we go further, n k minus 1, and now I think this is strange. We have 2 balls. We have now n boxes and k minus 2 balls to place in them. That is just n choose k minus 2. And these two balls can these two balls have k minus 2 choices to go into. So for both of these balls, we multiply this by 2, by k minus 2. So k minus 2 square. That is a bit complicated, but I think that is correct. So for something like this, for some general thing like this, we would have n, let's say n is the total number of boxes, k is the number of balls that we have, and any box can have any at max k number of balls. Yes, all the balls can be put into one box. Then we would have the answer. Let's write it in summation form. Summation n 1, not 1, I, ni, I will range from 1 till k, and we multiply this by k minus I power I. Yes. Hmm. Makes sense. Does it make sense? Yes, I think that makes sense. When I equals 2, we should get this thing. When we put I 2, or I equals k minus 2. When I equals k minus 2, we should get this thing. So I is k minus 2, and k minus, no, that is not correct. That is not quite correct. So a better way would be to write this as factorial I equals 1 till k n, or yes, minus I to k minus I power I. So when we put I equals 2, we will have n k minus 2 and k minus 2 square, which is the thing that we calculated here. So that is cool. That is cool. Let's see what smart thing the book says. Okay, we can calculate. We can calculate the answer. Can we like find, can we squash, can we squash this series into a singular formula? That would be cool. We have this thing. Can we find a singular formula for this? Like here we have to find solution to every term and then add those terms. Let's first of all verify if our formula is even correct. For k equals 2 and n equals 5. For k equals 2 and n equals 5. This formula becomes n I goes from 1 to 2, 5 I 2 minus I power I. Okay, so for I equals 1, this thing would mean, and this is summation, this is not a backwards 3, 5 choose, this is k minus I. K minus I is for I equals 1, 2 minus, this is 2 minus I equals 1, we have 5, choose 2 into, this will also be 2, this will be 1 and raised to some power 1 plus 2, choose 0, okay, hmm. I think the formula is messed up. Okay, I think this should go from 0 to k minus 1, which is 1. I think that, yes, I think that is correct. I goes from 0 to k minus 1. I goes from 0 to k minus 1. In this here, I is equal to 1, and here, let's say I will equal to 0. And when we have that, 5 choose 2 into 1 because I is 0. So this term gives us 5, and this 5 choose 2, which you calculated above, gives 10. So we have 15, which is correct. 15. So I guess the formula is correct somehow. Okay, and what do they say in the book? The process of placing the balls in the boxes can be represented as a string that consists of, and I have gone through this before in one of the streams. This still seems strange. The process of placing balls in the box can be represented as a string that consists of symbols O and a rightward arrow. Initially, assume that we are standing at the leftmost box. The symbol O means that we place a ball in the current box. Okay, we start with the leftmost box, and the symbol arrow means that we move to the next box to the right. Using this notation, each solution is a string. Okay. O means that whatever box that we are at, we place one ball there. And arrow means that we move to the right. Okay. So what do we know? We will, of course, have k number of balls. And the number of arrows can change from 1 till at max n. Hmm. No, no. The number of arrows is n. We have n number of arrows because let's say we want to place all the balls in the first box. We can just put all the, have a sequence like this, a bunch of zeros, which would mean place all the balls here, and then a bunch of arrows, so that we just go to the rightmost box without placing any balls. So that is cool. So in total we have this thing. Here we have k number of balls and n number of arrows, or n minus 1. I think n minus 1 number of arrows, because let's say we have 3 balls, 3 boxes, and we start here. We use one arrow, we got here, we used another arrow, and now we are already at the last box. So which is 3 minus 1. We used 2 arrows, 3 minus 1, n minus 1 arrows. Okay, and now we have to choose some way to rearrange these things. And that is equivalent to something. We have n minus 1 arrows. We have n minus 1 arrows, and we have k balls. And we have to place these k balls at n positions. Oh, yeah. But they can also repeat. They can also repeat. So yeah, that is a bit difference. Using this notation, each solution is a string that contains k times the symbol this and n minus 1 times the symbol arrow, which we did discover. So that is cool. That is similar. For example, the upper right solution in the above picture, this one can be represented by, we start here, then we use one arrow, we got here. We have one arrow till now, then we used another arrow, and now we are here. We used two arrows till now, and then we placed a ball, then one more arrow, then we placed a ball. So arrow, arrow, ball, arrow, ball, arrow, arrow, ball, arrow, ball, and then one arrow to go from here to the last ball, to the last box. This, the number of solutions is this. It is just this. Okay, shit. Okay, shit. Why? Okay, shit. That makes sense. That makes a lot of sense because in total we have k balls and n minus 1 arrows. So therefore, in total we have k plus n minus 1 places, and we want to put k balls into this many places, which is k plus n minus 1. Choose k, which is correct. Okay, and when we have found this, this gives us to choose k positions, to put k balls from k plus n minus 1 positions. And if there is a position which we didn't choose, then automatically we can suppose that we placed a arrow there instead of a ball. That is cool. That makes sense actually. And okay, that makes sense. So for the first one was very straightforward, direct formula, coefficient n of k. Yep, n choose k. And second scenario was a bit tricky. We found our own formula, which was this. Our formula was this. This is summation. This is not backwards 3. This is summation. I goes from 0 to k minus 1. And at every level, we find n k minus I multiplied by k minus I power I. But the book gave us a better solution, a more elegant solution, and they said that the summation of this series equals n minus 1 plus k choose k. That is cool. That is, this thing equals this thing, and both of these things have a different framework through which we reached this formula. And when we have something like that, we call that isomorphism. We have isomorphism in these two things. So this is isomorphism between these two mathematical frameworks. We can convert one into the other without losing any logical information. Cool. Now, scenario 3. Each box may contain at most one ball. Okay, and in addition, no two adjacent boxes may both contain a ball. No two adjacent boxes may contain a ball. For example, there are 6 solutions. Okay, we will not look at the solution. We will try to find the solution on ourselves. on our own. So what is the condition? There are n boxes, k balls. And for this one, let's actually write some formula because it has been so long. We haven't written anything. Okay, keywords. And keywords, CD concepts, combinatorics. Okay, CD combinatorics, n balls and boxes.cpp. But before writing the program, we have to create a theory, which we can just write. We have to first create a theory. If we have n total boxes and k balls, and we cannot put two balls together, we cannot put two balls together. Let's go with a simple example when n equals 4 and k equals 2. We have two balls, one here, one here. For every ball, I have to have a buffer. Or I could say every ball takes two boxes, right? We can say that. Every ball takes two boxes. If every ball takes two boxes, can I just put this equal to 2k n 2k and find the number of ways to choosing 2k things? No, no, no. Because the answer for this thing, if I calculate this thing where n equals 4 and k equals 2, this would turn out to be 1. But here the answer is not 1 because there is this wonderful representation, but also there is this way, this way to place the balls, and also ball, box, ball. So answer is 3 for this, not 1. So that is wrong. So what do we do? What do we do? We have n balls, n boxes. Johnny von Neumann would have been able to find the answer for this thing instantaneously, as if he was born with it. He was an amazing guy, like one of the best people. We have n boxes and k balls. What do we do? Every ball that we place at some point has to have a buffer to the left and right where no other ball can come. Try lead code 124. Yo, what's up? Today is your contest. How are you? Today is your hackathon. Good morning, by the way. Shit, you just woke up. I guess it is not even 3 o'clock there. It, let me see. Lead code 124. I didn't sleep. Shit, excited for the hackathon? 124. I have a flight on 7 a.m. Okay. Wait, you are going from New York to Massachusetts by a flight? This is the wrong question. I thought they're like close enough. 124. Okay, shit. It is a hard one. It is a hard one. A binary path. A binary tree is a sequence of nodes and binary tree. I am not planning. Tomorrow I'm going to do a stream in which I will write binary tree, a class in C++ which applies all the binary tree operations, insertion, deletion, finding the minimum, finding the maximum, and predecessor, successor, and also writing the whole thing in post order pre-order, and in order format. So tomorrow's stream is going to be fun. Each pair of adjacent nodes in the sequence has an edge connecting them. A node, the path sum, the path sum of a path is the sum of the node's value in the path. Given the root of a binary tree, return the maximum path sum of, okay, so the tree that I'm referring to tomorrow is going to a binary search tree. Wait, this is also a binary search tree. No, this is not. Here we have minus 10, but the right value is greater than minus 10, but the left value is also greater. So this is not binary search tree of any non-empty path. I guess this will use recursion. Cool. I thought of going via train, but it is chaotic. Okay, flight is cool. Okay, you have to go at 7 and you didn't sleep. Okay, excitement, I guess. And for this problem, my intuition is that recursion, just like feels like recursion. Here, when we'll start from the root and we will find what is the binary best maximum path from this thing and maximum path for this thing. But this isn't this just going through all the elements? Yes, this is going through all the elements, but that seems to be the way to do this. Find the best possible answer for this, compare the two, add the maximum one to this thing and return it. And for this, compare the two that are connected to this. And if they are the left and right things are null, then null, then return the node's value. And if only one of them is null, then add the value of the node, or just if one of them is not null, call the function recursively on that node and get its value, add that to your current value and return it. And I think that is cool because we are going through every node only once. And I think we don't even need memoization for this because there is no cycle. We don't even need memoization. That feels like the right way. And back to this solution. We have to find solution for this. I looked at the solution just now below, but okay, I can forget it. Here we have n boxes and k balls, and we cannot put two balls together. Okay, shit. Okay, when I have k balls, then I will have used k minus 1 boxes in between them. If I have a ball here, then I must have, if I have a ball here, then I must have a box here. And I have in middle some place. I might have a box or might not. But what I'm guaranteed to have is one box here between these two balls. So from n, I have used this many number of boxes are remaining. And how many places are there to place these boxes? There would be k plus 1 places to place these boxes. Yes, k plus 1 places to place these boxes. But yes, there is also a little thing. We cannot directly use this formula. K plus 1, n minus k plus 1, choose k plus 1. we cannot directly use this formula because of this. Let's say we have a ball here and a ball here and a mandatory box here, and then we have one box here and one box here. Let's call this box number 1, box number 2. That is cool. And mm, I have, these are extra boxes. These are extra boxes, and there are, I can put them here, I can put them here, I can put them here. Okay, and these are, well, 3 in this example, which is just k plus 1. So I have k plus 1 choices and k plus 1 things, and from k plus 1 things I have to choose n minus k plus 1 things. I think that is the formula. That is not the formula. Okay. Excitement plus tense. I'll be competing with many good coders. That is cool. I have a team of me and a girl. I kind of got excited. It will be fun. I will be getting a good experience. Yes, you will be getting a good experience. When I was in my 11th standard, even when I was at the end of my 12th standard, I didn't even know how to print hello world in Python. And you are doing lead code in C++ in 11th standard and going to a hackathon. That is amazing. And it is a Web3 hackathon. I guess, I believe, if I remember correctly, this is going to be cool. Pretty cool. You will learn and you will have fun. And it's, you are going to Massachusetts. Guess you can even visit MIT there, the campus. Yep, Web3. That is cool. I don't know about Web3. I know nothing about Web3. So I will learn about Web3 next year, but I guess Web3 is cool. Web3 is cool. And yes, I have a question. I have a question. Are you in the Discord? Is your name Zerth? Zerth? I suspect that is you because given the times, given the time difference, like I suspect that is you in the Discord. Shit. Okay. Okay. I had a theory. Okay, it didn't work. My bad. That is someone else. I don't have a Discord. Okay, that is unexpected. Okay. That is kind of unexpected. I would thought you'd have a Discord. You are getting into these nice technical things. Hmm. Yep. Discord. Yo. Okay, shit. Bro is into shady business. Telegram. And there are stuff. And there is a lot of stuff in Telegram. Okay. Yeah. So why does this formula work? And back to combinatorics. In this scenario, you can assume that k balls are initially placed in boxes and there is an empty box between each adjacent ball, uh, between each two adjacent boxes which have balls. The remaining task is to choose the position for the remaining empty boxes. There are n minus 2k plus 1. 2k plus 1 boxes that are remaining and k plus 1 position. Okay, k plus 1 positions makes sense, but why do I have shit? Okay, yes, of course. Okay, so our formula was correct. This is the correct number of positions that we have k plus 1, but the number of boxes we have used k minus 1 boxes. We have used k minus 1 boxes to place between the balls, but we also used k boxes to place these balls in, right? So in total, we used 2k minus 1 boxes and we had n boxes. So now we have n minus 2k plus 1 boxes remaining and k plus 1 positions. So that is the formula. That works. That works. Cool. That works. Yep. Yep. I'm thinking about making something of Defi. What is Defi? I don't know about Defi. Defines decentralized finance. Shit, that would be cool. That would be cool. I want to like get into this thing. Decentralized finance, blockchains, and everything because I do not understand any of this. How are contracts made and stuff happens. It would be like actually very cool. Actually very cool. Hey, yeah, I will get into this when I reach a rating of 2000 in code forces. It would be cool. Decentralized finance. And I guess we can also make a lot of money by creating bots. I have seen this guy who does online trading with bots that he created himself. Yeah, like, yeah, Mr. Robot. Of course, Mr. Robot. We have Mr. Robot here. Uh, he is Moondev, this guy. He does streams about this thing. His daily live stream, 8 a.m. Eastern UTC, Universal Time. Yeah, he makes bots and he does trading on them. Look at this. How many windows are open there? What the heck is happening? And these are all the trades that his bots are making. I do not understand any of this. So we will have to get into this at some point. That would be cool. App, Aptos. Okay. Not right now. Right now, I'm just doing competitive programming. And for this question, recursion is the thing that I think is correct. And yep, I actually want to get to Catalan numbers and solve as much as I can, or not solve, but go through as much as I can in this chapter on combinatorics. And it would be really cool if I could complete this whole chapter today. Let's go. The Catalan numbers. No, 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 no. Multi-coefficients. I've heard that term in in one of the streams that we did. Equals the number of ways we can divide n elements into subsets of size k, k1, k2 till kn, where the sum of them equals n. Multinomial coefficients can be seen as a generalization, as a generalize, generalization of binomial coefficients. If m equals 2, the above formula corresponds to binomial coefficients. That makes sense. Binomial, multinomial, binomial, multinomial. And now Catalan numbers. This is cool. Catalan numbers. I have isomorphism. Isomorphism. I've seen isomorphism in Catalan numbers. There is a thing called DYCK, Dick, Dick paths, which just gives series of Catalan numbers. There's this problem about parentheses expression. So parentheses P And there is this problem when you have a polynomial or polygon, let's say of 5 sides, then how many diagonals can I create here without any two crossing them, like this. Here I can only create two diagonals without making them cross each other. If I were to create any more diagonals from either this point or this point, then they would cross these, and I do not want that, right? If I did this, it would be crossing this one. That is bad. If I did this, it would be crossing this one, which is bad. So I can create diagonals like this, and also I can create diagonals like this, and essentially I can just rotate this thing, this point to all the 5 points available. So in total, I have 5 ways to create a diagonal in this. And this problem, I don't know the name of this problem, but this also gives us Catalan numbers. This also gives us Catalan numbers, and the formula for calculating Catalan numbers is n divided by n plus 1 and n factorial divided by 2 factorial or something. Shit, I completely forgot. I think it is 2 factorial. Yeah, so basically the thing is, we have this problem of making diagonals, this problem of parentheses, and this problem of finding dic paths. Dic paths are defined by something. And then there is the problem of binary trees, which also relates to Catalan numbers. So we have 4 things which all relate to Catalan numbers, and all of these 4 things can be converted into each other. All of these 4 frameworks can be converted into each other, and this phenomena is called isomorphism. That is cool. And yeah, so we can just begin reading about Catalan numbers. Catalan numbers Cn. Okay. Yeah. The Catalan numbers Cn equals the number of valid. It is not, yeah, it equals, but also, yeah, it is one of the things that Catalan numbers represent. So Catalan number Cn equals the number of valid parentheses expressions that consist of n left parentheses and n right parentheses. For example, C3 equals 5. When I have 3 left parentheses and 3 right parentheses, then there will be 5 ways in which I can make a valid expression of these parentheses, and these are the 5 ways. And this number, these numbers C1, C2, C3, C4 till nth, these are called Catalan numbers, and these Catalan numbers is like the pi or the most important series in combinatorics, which is cool. Parentheses expression. What is exactly a valid parentheses expression? The following rules define rules. The following rules precisely define all valid parentheses expressions. These are the rules which must be valid for a expression to be valid, which must be true, which must hold for an expression of parentheses to be valid. An empty parentheses expression is valid when we do not have any parentheses, okay? An expression A is valid, then also the expression, if you put 2 brackets around A, then that thing is also valid, okay? If expression A and B are valid, then also the expression AB is valid. Okay. Okay, sure, we can begin. Let's say we have three left parentheses and three right ones. So from the first rule, we see that empty thing is also a valid thing. So let's call this empty thing X, or this thing not E. Why did I forget the name of this thing? This is empty null. Let's call this null expression in which we do not have any parentheses. And from the first rule, it is valid. Now, from the second rule, E, and if we provide parentheses on both the sides, this thing is also valid. And since E is empty, we can this, write this thing as this. So this is also valid. And we can, since this is valid, let's call this A. And from the third rule, we can see here, if A is valid, B is valid, then AB is also valid. Let's call B is also A, then this and this, these are also valid. And I think, yeah, not just that I think, but we should be able to reach all of these parentheses just following these rules. Let's try to reach one of them. This one, let's go with this one. We have already found this, right? We have already proved that this is valid. Let's call this thing X. And if X is valid, then X and parentheses is also valid, then which is just this thing. So this thing is valid. And we can reach all of these from these three rules. That is cool. That is cool. Another way to characterize valid parentheses expression is that if we choose any prefix of such an expression that it has to contain at least as many left parentheses as right. Left can be higher, the number of left parentheses can be higher, but not lower than the number of right parentheses. In addition, the complete expression has to contain an equal number of left and right parentheses. And if we think of this thing, if we have a count, let's say, and we have our above expression, and whenever we see a opening parentheses, we will increase our count by 1. So initially we are here, our count is 1, and we see another opening parentheses, we increase our count by 1, our graph goes up. And whenever we see a closing parentheses, we will decrease our count by 1. So we are here, and opening here, and closing, and then closing. No, then closing, and it did a mess up somewhere. Here count was 1, here it was 2, here it was 1, here it was 2, here it was 1, and here it is 0. So initially, before the expression, we start with 0 and we end at 0. Since at every point the number of left parentheses has to be equal to or greater than the number of right parentheses, this graph can never be negative. If it is negative at any point, then boom, it does not work. So this has to be always positive or 0. We are considering 0 as positive. No, we are not considering 0 as positive. We are considering positive and 0 as the value of C to be correct. That is cool. And also the number of left has to match the number of right parentheses. Therefore, we start at C equals 0 and we will end at C equals 0. So that is cool. That is cool. That is isomorphism. And I will have to go to the washroom. I'll be right back in a minute. I'm back. And yeah, Catalan numbers. Yep, drink water just after coming from the washroom. Catalan numbers, we have a couple of formulas. Formula number 1 for calculating Catalan numbers, Cn should be equal to summation of C1, Ci and Ci and Cn minus I minus 1. And I goes from this to this. And not just summation, we are multiplying these two and adding. Why does this recurrence hold? The sum goes through the ways to divide the expression such that both paths are valid expressions. C0 and n minus 0 minus 1 n minus 0 minus 1. Okay, and we are multiplying the two. We are multiplying the two. And this is very, of course, this is very similar. This is similar to, or not similar, we could say, use the term isomorphism. This is very isomorphic to this thing. What we have here, matrix chain multiplication. In this, we have the recurrent formula. The recurrent formula of this. Here, instead, I and j are the things. I and j are the boundaries, and k is the one that is going from I to j. And here also we have that. Here the boundaries are 0 and n, and I is going from 0 to n minus 1. And we are multiplying the last two together. And this is also like very similar to that. Yeah, isomorphic. But that one also has some overhead, so we cannot just do that. We have to do some addition and multiplication there. But this is the thing. Yeah, does that make sense? Does this thing makes sense? They are saying if I have 5 left and 5 right parentheses, it is going to be equal to, let's say I have two things here, then two things here, and two things here, two here, and two here. These two, these two, these two, these two are ones, and these two are ones. Okay, and when I choose I equals to 0, what does this mean? When I choose I equals to 0, it means I am creating a valid parentheses, a valid expression that ends here, and I am multiplying that with the number of ways to create a valid parentheses given 4 left and 4 right parentheses. That makes sense. And then my I moves over to the next injunction to 1, 1, and we find the number of ways, the number of Catalan numbers, the Catalan number C2 and C3, and we multiply the two. Then we move here, I equals 3, and we find C3 into C2. Then we move here, and we have C4 into C1, and that is the last one. That is the last one. We do not move here because that is the thing that we are trying to calculate. That is cool. Ci, the number of ways to construct an expression using the parentheses of the first part, not counting the outermost parentheses. Cn minus I minus 1, the number of n minus I, n minus 1 minus I, the number of ways to construct an expression using the parentheses of the second part, which is the same as this. whenever we are at some I value, we find the number of ways to construct parentheses on the left part and multiply that with the number of ways to construct a parentheses, number of ways to construct valid parentheses on the right part, and we multiply the two. And our I goes from 0 till the last one and minus 1. We do not go till past the last because that is a thing that we are trying to calculate. So that would create a loop and we do not want that. We would never find an answer for that. The base case is C0 is 1. When we have no parentheses, then there is only one way to represent them, which is an empty parentheses. Because we can construct an empty parentheses expression using 0 pairs of parentheses. That makes sense. And formula 2. Catalan numbers can also be calculated using binomial coefficients. Yes, this is the formula that I was messing up earlier. Somewhere around here. Yep, this is the formula. So the correct formula is n plus 1 factorial n plus 1 n2 2n, choose n divided by n plus 1, and this thing somehow works. Okay, let's see what this means without reading the thing, without reading the book. Let's see what this means. 2nn. Wait, I saw a video which explains why this thing works, but I forgot. Okay. 2n plus 1. This gives us how many ways can we choose n things given 2n things. Okay. And then we divide that by n plus 1. Okay, we will have to read. I am not getting any ideas how this thing would give us the nth Catalan number. Why Cn would equal to this thing. Let's see, there are a total of 2n. The formula can be explained as follows. There are a total of 2n. Choose n ways to construct a not necessarily valid parentheses. That makes sense. That makes sense because I have n left parentheses and n right parentheses. Therefore, I can say I have 2n locations, and in these 2n locations, I have to put, let's say, the left parentheses. I have to find n locations to put these left parentheses, and every location where I didn't put a parentheses, that automatically defaults to putting a right parentheses there. So the total number of ways to put parentheses would be 2n, choose n ways, but all of these are not necessarily valid. Though the number of, at the end, the total number is true. At the end, the total count of left and right parentheses is equal because we are taking them both equal to n. So that is ways to construct. There are a total of 2n, choose n ways to construct a not necessarily valid parentheses expression that contains n left parentheses and n right parentheses. Let us calculate the number of such expressions that are not valid. That makes sense. If I can calculate then just reduce from this expression the ones that are not valid. Okay, how do we do that? If a parentheses expression is not valid, it has to contain a prefix where the number of right parentheses exceeds the number of left parentheses. Yes, the idea is to reverse each parentheses that belongs to such a prefix. For example, this is invalid, contains a prefix this, which is invalid. And after reversing the prefix, this becomes this. we reversed the prefix. Okay, we reverse, and by reversing the prefix, they mean reversing these brackets individually, these parentheses individually. This one was a right opening parentheses, it became a closing one, and these two were closing parentheses, they became opening parentheses. I guess that is what they mean by reverse. The resulting expression consists of n plus 1 left parentheses and n minus 1 right parentheses. Yes, n plus 1 left parentheses and n minus 1 right parentheses, because we had one, this whole thing, because in this prefix we had one extra right parentheses. When we reversed, we had now in this prefix again one less right parentheses, so n minus 1 and n plus 1 left parentheses. That makes sense because we flipped one extra right into the left one, so left increased from n to n plus 1 and right number of right parentheses decreased from n to n minus 1. The number of such expressions is to choose n plus 1, which equals the number of non-valid parentheses expressions. Thus the number of valid parentheses expression is this. Wait a minute. The resulting expression consists of n plus 1 left parentheses and n minus 1 right parentheses. Yes, that I agree with. But the number of such expressions is this, which equals, why would it be equal to this? It would be equal to this because now I am finding, it would be equal to this because now I have n plus 1 left parentheses to place n minus 1 left parentheses to place at 2n positions. That, okay, yes, yes, because now I have n plus 1 left parentheses and 2n total positions, so I will have 2n choose n plus 1 ways to put these left parentheses here. Okay, so we just subtract this from that. Okay, let's do that. The total number of v's are 2n, choose n, and these are not all necessarily valid, so we have to subtract 2n, n plus 1, and these are the bad ways. We do not want this, we want some of this, and we want to reduce this from this. And okay, how do we write this? 2n n minus 2n minus 1, I guess 2n minus 1, 2n minus 1, 2n plus 1 and 2n plus 1 and subtract 2n minus 1 n. That is not very pretty. No, that is not very cool, is it? Let's write this in terms of the factorial. So we have 2n factorial divided by n factorial square minus 2n factorial divided by n plus 1 factorial into 2n minus n minus 1, which is n minus 1 factorial. Okay, we can take 2n factorial common, and what will we have? We can write this. Yeah. Yep, here we'll have n factorial into n factorial, and on the right we will have minus 1 divided by n plus 1 into n factorial, and here n minus 1 factorial, and we can take this n factorial common from both the sides, which, yes, n to n factorial divided by n factorial, and we cannot just cut this. We cannot cut these two, this from this, because we have 2n factorial, not 2 into n factorial. And here we would have inside n fact, we can write n factorial as n into n minus 1 factorial. Yep, minus 1 by, here we have n plus 1 into n minus 1 factorial, and now we can take this n minus 1 factorial common from both the sides. We will have 2n factorial divided by n factorial into n minus 1 factorial. N minus 1 factorial is also here, and divided by 1 by n minus 1 by n plus 1. Yep, and now we have, yes, the writing is absolutely amazing. Here we have n factorial into n minus 1 factorial, and here n plus 1 minus n divided by n square plus n. We can just, yes, n square plus n, we can just take n common. Yes, that is correct. So 2n factorial, here we will have 1 remaining, divided by n factorial into n minus 1 factorial into n plus 1 into n, and this n can be multiplied by n minus 1 factorial, and it becomes n factorial. So we have 2n factorial divided by n factorial into n factorial into 1 by n plus 1, which can be written as 2n choose n into 1 by n plus 1. So that works, but this guy was able to do this in a single line, and not, he didn't took this much space. So thus the number of valid parentheses can be the expression this. Okay, now what do you do with this? You can, okay, you can do this thing into this. If these two are true, is this is the tree thing that I was referring to before. 2n plus 1, 2n not divided by 2n choose n plus 1. We can rewrite this as n into n divided by n plus 1 into 2n choose n. How does that work? N plus 1. I think that does work. 2n factorial divided by n plus 1 factorial into minus 1 factorial into 2n minus 1 n minus 1 factorial. If I multiply by n in the numerator and the denominator and take this, we will have 2n factorial, and also take n plus 1 from here. We will have 2n factorial into n factorial into n factorial into n plus 1, and we have this numerator multiplication from above, and this thing equals 2n, choose n, and on the right we have this n divided by n plus 1. So that is correct. That is cool. And then you can take 2 and choose n common from both the things, and you will have this thing. That is cool. That is cool. That does work. And Catalan numbers can be used in counting binary trees. How many number of binary trees are possible when the height is something? When the height is 3, when we have 3 nodes. Okay, when we have 3 nodes, how many possible configurations are there for binary trees? The rooted, okay, non-rooted or rooted. There are 2 versions, but for both, the answer is 5. The third Catalan number. There are Cn binary trees of n nodes, and there are Cn minus 1 rooted trees of n nodes. So that is just isomorphism. The concept of Catalan numbers can be applied to parentheses, to counting trees, binary trees, and other things. That is cool. And now we can move on to inclusion, exclusion. Holy shit, I just joined the stream and I see the giant whiteboard drawings. Haha. Okay, cool. Yep. Now we can move on to inclusion, exclusion principle. And it has been 3 hours and we have only done binomial coefficients and Catalan numbers. Yep. Binomial coefficients and Catalan numbers from combinatorics, and I really want to get to inclusion and exclusion. And what do we have after that? Burnside's lemma, and then we have Cayley's formulation, and then Prussier code, Prussier code. Okay, let's at least do, okay, not just at least, we will do inclusion exclusion, and then we will do for sure. Okay, do I have to say, and do I like actually want to say that we will do, we will for sure complete inclusion exclusion, but do I want to say that we will for sure complete this Burnside's lemma in comprehensive manner? Okay, let's go. Okay, we will do at least these 2 things. We will do these inclusion exclusion and then Burnside's lemma, and by the end of this we should be able to write inclusion exclusion principle or explain it in terms, in like in some way at some comprehensive level, in no matter what state we are in, right? That should be the goal, I guess, when we are studying. Cool. Inclusion exclusion is a technique that can be used for counting the size of union of sets when the sizes of the interactions are known and vice versa. A simple example of the technique is the formula this. Okay, inclusion exclusion is a technique that can be used to for counting the number of for counting the size of a union of sets when the sizes of the intersections are known. Okay, that is simple. That is very simple. If I have a bunch of sets, right, I take their union, I can use inclusion exclusion to find uh, their size, the size of the union. But for that, I need to know the sizes of their interactions, these sizes. Okay, where A, B are sets and x bar denotes the size of x. The formula can be illustrated as this. Okay, since we already said that we know the size of their intersections, so the size of the union is going to be the size of A plus the size of B, subtract the size of intersection of B, and that makes sense. Like if we were to actually take A and we take B and we do B and A, if we add their sizes, then, well, when we added A, we added this whole area and also this whole area, and then when we added the size of B, we added this whole area but also this area again. So we have to do some subtraction. What do we have to subtract? We have added this area twice, so we have to subtract this area, and this area is equal to the size of their intersection. That makes sense, right? That is inclusion exclusion for two things, and for two things it is like we don't even need a principal inclusion exclusion principal technique. We can just visualize this, so it is easy to see here. But when the number of sets gets greater than 3, it is even easy at 3. When we are at 3, it is easy to see this thing is added twice, this thing is added twice, this thing is added twice, this thing is added thrice. So we have to subtract this 2 times. But when we get to 4, when we have 4 sets, it is even hard. It is very hard when we have 4 sets. Let's say this is one of our sets, this is one of our sets, and this is another of our sets. Where do I put the fourth set? The fourth set, let's go say, goes here. How do I calculate the size of the union? It is very messy. It is very messy. So then I guess we need inclusion exclusion. Our goal is to calculate the size of the union A union B that corresponds to the area of the region that belongs to at least one circle. That corresponds to the region that belongs to at least one circle, and also the area that belongs to both the circles, because it is at least one circles. The picture shows that we can calculate the area of A union B by first summing the areas of A and B and then subtracting the area of the intersection, which makes sense. The same idea can be applied when the number... Okay, wait. Okay, let's first read, because my doubt is inclusion exclusion just saying include everything and then exclude something? Is that the whole thing? Or let's see. The same idea can be applied by the number of sets when the number of sets is larger. When there are 3 sets, the inclusion exclusion formula is add everything, subtract 2 things, then add the 3 things, the intersection of 3 things. So does it go plus minus plus minus? In the general case, the size of the union, this thing, can be calculated by going through all possible intersections that contain some of the sets. In general case, the size of union x1 union x2 union x3 till xn union can be calculated by going through all possible intersections that contain some of the sets. All possible intersections. And how do we know which intersections to add and which to subtract? I guess first you take, let's say, intersection of only one set, which is just A. When you are taking intersection of a set with itself, the size is 1, and you start with addition. You add all of those. And when you start taking intersections of sets of 2, then you subtract the thing. And when you start taking intersections of 3 sets, you add again. And when you start taking intersections of 4 sets, then you subtract again. And then you add again when you are taking intersections of 5 sets. That is a theorem, I guess. Otherwise, the size is subtracted from the answer. If the intersection contains an odd number of sets, its size, shit, odd even. So you can look at it in terms of odd even. That, I think that makes sense. We can look at this in terms of odd even also. Let's say there is some area. Let's have 3 sets. We have 3 sets. We have this area, first of all, which is only covered by one set. So one set is even, one set is odd. And then we have this area, these areas, which are covered by 2 sets, which is odd. And then we have this area, which is covered by 3 sets, which is even. So when we add all of these sets up, all of these areas which have odd things, which are a sum of odd, which are all of these areas which are a part of even number of sets. All of these areas we subtract them, and all of these areas which are part of odd number of sets, we add them. And why do we do that? Why do we do that? Why do we do that? Do that. We do that. Why do we do that? Okay. Well, in this formula, it says that we just do that. But why? I guess there is some geometrical explanation for this, and I can kind of see why that would be true. Because when we are subtracting this part, we are also subtracting this part, and when we are subtracting this part, we are also subtracting this part again, and when we are subtracting this part, we are subtracting this part again. Therefore, we have subtracted this part odd number of times, but this part was overlapped odd number of times, and that odd number is 3. So we added this area 3 times and we subtracted this area 3 times. Now we have to add this area back 1 time to get this area. That, I think, is a fine explanation or adjustable explanation. And now derangements. What are derangements? As an example, let us count the number of derangements of elements 1 to n. What are derangements? As an example, let us count the number of derangements of elements 1 to n. That is permutations where no element remains in its original place. Okay, the number of permutations where no element remains in their original place. For example, when n equals 3, there are 2 derangements. Okay, I guess we should be able to come up with a formula for that. If n is something, then for every nth number, I have n minus 1 positions. For every number, I have n minus 1 positions. And Yeah. So, or we can see every position has n minus 1 candidates which can come there. So I guess n minus 1 factorial. Just yes, n minus 1 factorial should be the answer. One approach for solving the problem is to use inclusion-exclusion. Let Xk be the set of permutations that contain the element k at position k. That contain the element k at position k. So when n equals 3, the sets are as follows. The sets are as follows. What do we have here? Okay. Approach Xk be the number of positions, be the set of permutations that contain the element k at the kth position. To okay. X1 1. That is the number of ways in the number of permutations in which one is at the first position, and X2 is the number of ways in which 2 is at the second position, and X3 is the number of ways where 3 is at the third position. Using these sets, the number of derangements equal the total number of permutation minus the union of all of these sets, okay, which is what? So is this okay? It makes sense. We can okay, since we know inclusion exclusion now, we can write a formula for calculating this thing. Let's do that. We want to calculate n factorial minus this thing union or size of x1 union x2 union x3 union union xn. Yes, yes, right, that is the thing. Yep, that is the thing. So we have to write a formula for that. Hello, the world finals. What world finals? Shit, my phone is going to die. There are cricket world finals, I guess. I don't watch cricket. And hello, shit. Eric, my bad. I was unable to see the solution that you sent me, but I read the problem statement which you sent in Discord, and that is like literally the same. Okay, ICPC World Finals, my bad. I read the problem statement which you sent on Discord, and it is literally the same question. And the guy who was explaining the question, he said that there is a obvious way to solve this in nk log time or something that is better. He said there is an obvious way to solve this in this manner, and it took me, I guess, 20-30 minutes to come up with this nk log n method to solve the question. And he said there is the obvious way to solve this question in this time complexity. Okay. And yeah, I will have to watch it after very way, and it's going to be cool. And ICPC World Finals, shit, in Baku, right? They are happening in Baku, and there is also a push-up contest. I don't know about, not that I don't know. I know for a fact I won't be able to win ICPC World Finals. Able to win at this point, I see. But what is the push-up contest? Yep, push-up challenge. I can win the push-up challenge. I think I can say that with confidence. I will be able to win the push-up challenge because my personal PR. Why do I say personal PR? My PR of 6 push-ups. And I think no one there can beat that. 306 is pretty cool. Yeah. Let me fix this. Now charging. That's good. And derangements, number of derangements. Yep. Getting back to this thing. We have to write a formula for this. We can find this thing using a thing that we just read about for the first time, inclusion, exclusion. We can find this using inclusion, exclusion. So the thing was this plus this plus plus x n and subtract x1 intersection x2 and subtract all of those negative intersections and then add all the intersections, subtract all the intersections where we are taking intersection of even number of elements, even number of sets, and add all the intersections where we are taking intersections of odd number of sets, and that would give us the answer for this thing. I think the answer is better represented by n minus 1 factorial, because for every n we have n minus 1 choices, right? And for the next one also we have n minus 1 choices, not n minus 1 but n minus 2 choices now, because one has already been chosen there. So in total we would have n minus 1 factorial choices. Wait, wait. If this is true, if this is true, then we have n factorial minus x1 union x2 union till xn union equals n minus 1 factorial, and this would give us, let's call this thing x, big X. So x would be equal to n into n into n minus 1 factorial square. But I think this is only when these sets have a certain property to them, property of derangement to them. Yep, we applied inclusion exclusion in the example, in this example. Let's see, 4. Why is it 4? Yeah, answer is 2. Answer is 2, which is correct. 3 minus 1 is 2. 2 factorial is 2. That is cool. So the n minus 1 factorial formula is also correct. It turns out that the problem can be solved without using inclusion exclusion. Fn let Fn denote the number of derangements for 1, 2, and till n. We can use the following recursive formula. For n equals 1, there are 0 ways, and for n equals 2, there are 1 ways, and then the sum of the last 2 ways. So it is not equal to factorial. For n greater than 2, there are n minus 1 into Fn minus 2 plus Fn minus 1 ways. The formula can be derived by considering the possibility how the element 1 changes in the derangement. There are n minus 1 ways to choose an element x that replaces element 1. In each such choice, there are two options. Option 1, we also replace the element x with the element 1. After this, the remaining task is to construct a derangement of n minus 2 elements. We replace the element x with some other element, other than 1. Now we have to construct a derangement for n minus 1 elements. Okay, because we cannot replace the element x with the element 1 and all the other elements must be changed. Okay, that does not make some sense to me. Okay, I mean, it's been 3 hours and 17 minutes going through combinatorics, but I have to also complete this thing. Not complete, but have a comprehensive understanding of this. Burnside's lemma, Burnside's lemma, whatever it is. Okay, so in this part, we have to understand this thing, why this thing works. We know that we can apply inclusion exclusion here. We know what inclusion exclusion is. Inclusion exclusion is when there are, let's say you wanted to find the size of the union of some n sets. So what you do is you take intersection of elements of sets 1 of 1 sets, then you take intersection of 2 sets, then you take intersections of 3 sets, every combination of 2 sets, every combination of 3 sets and 4 sets, till you take intersection of all the n sets. And when you have intersection of odd number of sets, you add that, and when you have an intersection of even number of sets, you subtract that. Right? This this makes finding this makes finding the union very easy, and this might be like very obvious to some people, but this makes finding the union very easy, because I remember solving a question in a contest, and in there I had to take union of 4 things, of 4 sets, and find its size, and that was messed up. It took me more than an hour, but I was somehow able to come up with the formula which worked. And the thing, why does this work? Okay, we are doing n minus 1 into f of n minus 2 plus f of n minus 1. What is this? This is the number of ways to choose n minus 2 derangements, and this is the number of ways to choose n minus 1 derangements. Option 1. Okay, we do n minus 1 because we do this for n numbers, for all the numbers that can come to this current position, and there are n minus 1 choice for any given position. Okay, or we could say for any given position there are n minus 1 choices, right? And option 1, we also replace the element x with the element 1. We just replaced, right? And then we have to find the number of derangements for n minus 2 elements. That makes sense. That makes sense because we have removed x from its position for sure, and also we have removed 1 from its position. So now we have to find derangements for n minus 2 elements. Or option 2, we place the element x with some other element with some other element than 1. Okay, we have to construct a derangement of n minus 1 elements because we cannot place the element x, because we cannot replace the element x with element 1, and all the other elements must be changed. Okay, I don't get option 2. Option 2, we place the element x with some other element 1. Okay, we had, let's say, a few 4 elements, and element 1 was here, 2 was here, 3 was here, and 4 was here. Let's say we chose 4 and we brought 4 here. So we have this thing, and in our first position, in our first option, we put 1 here. Now derangement for 4 is solved and derangement for these two are solved, and we only need to find derangement of this, which is f4 minus 2, n minus 2. That is correct. And then option 2, we place the element x with some other element. We replace the element x with some other element other than 1. Now we have to construct a derangement of n minus 1 elements because we cannot replace the element x with the element 1. Because we cannot place the element x with the replace the element x with the element 1, and all other elements must be changed with some other element than 1. Okay, that would mean something like we had these elements initially 1, 2, 3, 4, and I chose 4 and I brought 4 here to 1's position. So now 1 is now removed from its original position, but we replaced 4 with a number 3. Now we have put, since some other number here, we have to find a place for 1. But yes, and 1 can go to any place that one likes. And we have also solved derangement property for 3, for 4 and for 1. Shouldn't this be n minus 3? No, 1 can go anywhere one likes. And how many positions are there? Okay, first of all, this element that we chose could be could have been chosen from n minus 2 elements, and not just that, this element itself could have been chosen from n minus 1 possible elements. And when we made our choice of this, we could have chosen n minus 2 possible elements to replace this. So n minus 1 to n minus 2, and after we had done that, we would have to find the derangement for multiply this by the derangement of f n minus 3, because at this point 1 is fixed, one of these is fixed, and the other 2 of these are fixed. No, 1 is dangling. 1 can go to n minus 2 positions. Ah, okay. I don't get this part. This option 2. Why does this option 2 works? We replace the element x with some other element than 1. Now we have to construct a derangement of n minus 1 elements. Of n minus 1 element. Why are things in this book written as if they are supposed to be obvious by just reading one line? I guess the reason is because when you read this, there is a very brief introduction to the topic, derangements, And now, since I know that there is a thing called derangements, I can go off to the internet and read about it comprehensively. And this just feels like I'm stupid because I cannot get this, but it is kind of designed that way. In a way, it is designed that way. Okay. Uh, Explain the still formula for number of derangements. Derangement nobody gets their own hat back problem. Shit, that is one way to define the problem of derangements, I guess. Let's go step by step and derive the recursive formula. Derive the recursive formula for number of derangements. Okay, what are derangements? What is a derangement? A derangement of n objects is a permutation where no object is in its original position. That makes sense. We usually denote the number of derangements of n objects as dn. Okay, that is our depiction. Sometimes called the subfactorial of n. Oh, this is a new notation. This is a new notation. Subfactorial. Okay, I'm going to use this. Okay, shit. I will use this with my friends and I will act as if this is the most natural thing to know. Subfactorial of n. Okay, we represent this like this. And dn, the number of derangements given n elements. Key idea. Take n labeled objects 1, 2 till n. Pick n objects, say object 1, and see where it goes. It can go to n minus 1 positions. It cannot stay in position 1. So it has n minus 1 possible places to go. Let's say object 1 goes into position k, where k is not 1, right? Now let's have two cases to consider depending on what happens to the object originally in position k. Okay, we are saying 1 goes to that place, 1 goes to k. So something happens with the thing that was at position k. Okay, case breakdown. Object 1, object k goes to position 1. So we just swapped n and k. We swapped 1 and k, and 1 is arbitrary. We are using 1 as just one of the elements from 1 to n. Then we say we have a swap between 1 and k, and the remaining n minus 2 objects must still be dearranged number of ways, number of cases for this. Okay, okay, that makes sense. That makes total sense. This is combinatorics or this is in case 2, object k does not go to position 1. So we have only fixed 1, but wherever it goes, it is going to fix something, right? Then we have object 1 in k position, and 1 and position still 1 still needs to be filled by some other object, but not k. Now we have n minus 1 objects left to derange with k position forbidden for object k since it is already taken, with position k forbidden for object k since it is already taken. That is just another derangement problem of size n minus 1. Okay, this thing I still don't get. And let me go to the washroom and I'll be right back in a minute. You totally back. And okay, why does this case 2 does not make sense? Because we have decided that this kth object does not go to position 1, and in a sense, so we have dearranged k and we have dearranged 1, and also we have dearranged some other object whose at whose place k is going to go. So shouldn't this be dn minus 3? That is just another derangement problem of size n minus 1. Then we have object 1 in position k, and position 1 still needs to be filled by some other object, but not k. Now we have n minus 1 objects left to be deranged with position k forbidden for k objects. Combining the two cases, this turns out to shit. ChatGPT can really write latex. That is cool. And base cases are these. Okay, I have a few questions. First of all, uh, since for each question we have n minus 1 elements to choose from, y choose from, and we have n positions in total, and at each position, no, 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 we don't have n minus 1 elements at each. Okay, not for each. For the first position, we have n minus 1 elements uh, to choose from, and for the second one we have n minus 2 elements to choose from, and so on till for the last thing we won't have any elements to choose from. No, 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 no. This is wrong. This is wrong. This is wrong. Because I cannot say this. Yes, I cannot say this. This is wrong. Because it is true that this first one has n minus 1 elements to choose from. Let's say it chooses the element k, which goes here. Then for this position, I have, since k is never going to come here, I have n minus 1 choices, not n minus 2 choices. And okay, so I think this one does not expand this formula. I don't get the second case. Okay. I don't get the second case. We say that k doesn't go to position 1, and then k has n minus 2 positions to go to. K has n minus 1 and minus 2 positions. Yo, yo, you are back. Hello. So k has n minus 2 positions to go to, and some and one of those n minus 2 elements is also going to go to this position 1, which which is not k. Yeah, question mark. I don't know. Question mark. This is the subtle part, and it is where most people trip up. Yes. Uh, yes, I am evidence. I am not evidence. I am witness. And it's where most people trip up when first seeing the recurrence. Let's slow down and untangle case 2 carefully. Recap of setup. We have n objects, 1 to n. Okay. We are building a derangement Dn. We pick object 1 and put it in some position k, where k is not equal to the first position. Okay. Okay. Now position k is occupied by 1. Object k still needs to go, but we are in case 2. So object k does not go to position 1. At this point, we have position 1 is still empty, position k is filled with object 1, and n minus 1 objects still remain to be placed. Everything except object 1. Yes, n minus 1 objects need to be placed, but not in a derangement manner, right? Not in a derangement manner. They just need to be placed. N minus 1 objects. Why this reduces to dn minus 1? That is a good question. Here is the trick. We can relabel the problem. Think of position k as no longer being special. It is just taken. Now we have a smaller derangement problem. Positions available. All positions. Shit. That that makes sense. That makes sense. That shit. Okay. I get it. I get it now. I get it. Okay. Eureka. Okay, we have, let's say, n things, and n equals 4. N equals 4. So originally we had 1, 2, 3, 4, and our derangement is defined as we have to move this one from the first position to some other position that is not 1. We have to move this 2 to some other position, but not its original position, which is 2, and move this 3 to some other position, and move this 4. Now, let's say we chose one of these positions to put this one element in. Right? Let's say we chose 3. 1, 2, 3, 4. Let's say we chose 3. And now we have 1 here. This is position 1, position 2, position 3, position 4. We have 4 here originally. We have 2 here originally, and 3. Now, let's say now there are two possible ways. This 3 can either remain here, or this 3 goes to some other place. When this 3 remains here, we have moved 1 from its original position of 1, and we have moved 3 from its original position of 3 to position 1. And now we only have to find the derangement for n minus 2 things. That is cool. But now let's say we do not put 3 here. Let's say we do not put 3 here, and these are the positions. 2, 1. We have 1 here, which is correct. We have 4, and we have 2, and we have a dangling 3. And this 3 has to go somewhere, and this 3 cannot go here, which is the definition of a derangement. This 3 cannot go here, this 2 cannot go here, this 4 cannot go here, which is the definition for derangement. And we can just ignore this part because this is already done. We can call this derangement of n minus 1 because one thing is already done. 2 cannot come here, 3 cannot go here, 4 cannot go here. So dn minus 1, and also n minus 2, dn minus 2. And in total, we have to do this for n numbers, I guess. Yes, we have to do this for n numbers. But no, we are doing this for n minus 1 numbers. First we fix this, then we fix this, then we fix this, and at last, do we have to fix this? I guess not, because we have already, since we have already fixed all the other ones, this has already gone through all the possible ways that this could have gone to. Yes, that is the view, that is the point of view framework which we can apply here. Okay, it now makes sense. Relabeling argument. Yep. Treat position 1 of this new element of this new problem as position 1 of the old problem. Treat k of this new element as position k of the old problem, but since it is already taken, remove it from consideration. Okay, this makes sense now. This makes sense. But now, why do we multiply this by n? The remaining n minus 1 objects must form a derangement of the remaining n minus 1 position. The number of ways is this. Okay, that makes sense. Now, why do we multiply this by n minus 1 instead of multiplying this by n? Combining the two cases, yes, I agree with n minus 1 and I agree with n minus 2. And how do we, if for each of the n minus 1 choices? Oh, makes sense. For any element 1, for any element 1, there are n minus 1 choices that one can go to. That makes sense. So dn equals n minus 1 into dn minus 1 plus dn minus 2, and we have a bracket here. Okay, that makes sense. 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 We choose any arbitrary number and we take it to some position k, and this, so we put our number, arbitrary number 1, at position k, and this kth element either goes to this 1th element, and if it does, then we have to find now derangements for n minus 2 numbers, because for 1 and k we have already found that we have already fixed their derangement problem. But if k does not go here, if k cannot go here, then we have to find solution for n dn minus 1 positions. So that would be the answer when I put 1 to the kth position, and in total there are n minus 1 kth positions where 1 can go to. So in total the answer would be this: n minus 1 into derangement of n minus derangement of n minus 2 plus derangement. What is this? I thought, why is there a eye is staring me in the face? This is dn minus 1. That makes sense finally. Okay, option 2 makes sense, option 1 makes sense, and everything makes sense. Okay, and the base case is also, when we have only one element, then there is no derangement. We cannot put the first element anywhere. When you have two elements, there is only one derangement when you swap the two, and if there are more than two elements, then this is the recursive formula. Makes sense. Now Burnside's lemma, whatever it is, you have to see that. It's actually, before moving on to Burnside's lemma, let's write a thing. Let's write this, a, a program in C++ to find this. And derangements dot cpp, it will return long, or derangements. It will take in an integer n, and yep, here we are. So base cases: if n equals 1, return 0. If n equals 2, return 1. Else in the else case, we call this function again. But we will also have a memoization map of int to long, and it will be memo. We do not have thing called map include map. Okay, uh, using namespace std. Okay, 7. Now if memo dot count n, then return memo n. Else if not, then end or long res equals initially 0 res equals n minus 1 multiplied by derangements of n minus 1 plus derangements of n minus 2, and let's add it to memo of n equals res, and then return res. Let's have our int main, int n, cin, n, and cout derangement is going to be equal to derangements of n with a new line. Cool. That does work. CD combinatorics. No shit. It's CD concepts combinatoric plan plus plus derangements. Let's run it and find the derangement for 3. It should be 2. It is 2. Wait. Enter the count. Clang not slash out. 2 is the count, and yes, then 3 is the count. Number of derangements is 2. And okay, so let's see. Um, I wrote a I wrote a program for okay, derangements for 1E7. Let's say extremely large, cannot be calculated directly. Shit. Okay, 1E5. Okay, shit, it is very big, it seems. Uh, for calculating the arrangements, give me a few test cases. Should this is like actually in the reverse way, instead of me telling AI to write a program and then I will be the one testing the program. Here I am writing the program and AI is testing my program. That is funny. 8 for 8 answer is this. Let's see. 14833 14833. That is cool. That is cool. Okay, so we can confidently move on to this thing, whatever it is. Burnside's lemma can be used to count. Okay, what is the lemma? The number of combinations so that only one representative is counted for each group for symmetric combinations. For symmetric combinations, Burnside's lemma states that the number of combinations is. What even is the thing that this is referring to? Burnside's lemma can be used to count the number of combinations so that only one representative is counted for each group of symmetric combinations. I do not know about symmetric combinations. What are symmetric combinations? What is Burnside's lemma? Burnside's lemma, sometimes jokingly called the lemma that is not Burnside's. Okay, is a powerful chat GPT is making pun. Okay, Burnside, not lemma that is not Burnside's is a powerful counting tool in combinatorics for problems with symmetry, especially when you want to count distinct configurations up to rotation, reflection, or some other symmetry. Okay, so, okay. I don't even get in which domain this is referring to. Symmetry problems, combinatorics for problems with symmetry. Yes, what is the problem that it solves? Suppose you have some objects, coloring arrangements, graphs, etc., but many of them look the same because a group of symmetries maps one configuration to another. Example, coloring the vertices of a square. Rotations and reflections may produce colorings that we consider the same. Huh. Okay, 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 okay. Naive counting would overcount because it treats rotated copies as distinct. Okay, we need a way to count orbits, that is distinct configurations under the symmetry group. Okay, that is what they mean by only one representative is counted for each group of symmetric combinations. Okay, it makes more sense now. We need to find a way to count orbits, that is distinct configurations under the symmetry group. Distinct configurations which even after rotating and just rotating, they do not look like each other. They are still distinct. Okay. Statement. What is the state? ChatGPT is using this box which looks really cool. Let G be a finite group acting on set X. Be a finite group acting on a set X. What is acting on a set mean? Then the number of distinct orbits, that is distinct configurations up to symmetry is this. X is the total set, and from that we are choosing G things. Is that it? We are choosing K things, and N is the total number, where G number of symmetries. One symmetry, likely rotation by no one. Count how many configurations are unchanged by each symmetry. Add them by the number of symmetries. Why it works? Okay, I don't get this part. Okay, first let's try to understand what the problem actually is, right? Then we can think of some solution to the question. So here we have a problem of arranging some n things, and what we are trying to solve is that some of those configurations might be the same under rotation. So we don't want to double count them and subtract them from the total number of configurations. Alright? Exactly, that is the core idea. One-side lemma is the symmetric way to do that without messy case by case subtraction. Okay, let's restate in your words. You have n factorial arrangements or okay, n factorial permutations, etc. But some of those look the same if you rotate, reflect, permute them according to some symmetry group G. Okay, so shit. Okay, the way that we define a rotation, permutation, a reflection is whatever way that we define. If we perform that rotation, reflection, permutation, or anything on some elements, on a element, on a set of configurations, we are calling that set G. When we perform these operations on any of those elements in this group G, we can convert them into each other. So therefore, they are all part of the group G. If we just count all raw configurations, you overcount. So what our thing, our idea is to, or our goal is to count the number of groups. If we just count all raw configurations, you overcount because you are counting each orbit of equivalent configurations multiple times, each per symmetry that maps it to itself. The naive way, you could try count all configurations, figure out which ones are duplicates under rotation, subtract duplicates, but figure out which ones are duplicates under rotation. Okay, naive way. Yes, yes, yes. But that quickly becomes messy because some configurations might be counted multiple times under different symmetries. Shit, okay, that is also a problem that we might go through. One-side's way. One-side's lemma flips the process. Instead of starting with all configurations and subtracting duplicates, it asks for each symmetry. How many configurations stay unchanged? That is a good question. Then arrange those counts. This avoids double counting, headaches, each orbit. Okay, okay. This, instead of starting with all configurations and subtracting duplicates, it asks for each symmetry how many configurations stay unchanged. If I can figure out how many configurations stay unchanged given a rotation, then I can arrange them. Yeah, this avoids double counting headaches because each orbit contributes exactly gn times. Okay, what is gn? What is gn? Here, the set G. No, they are not. ChatGPT is not group. What is G here? Is it? Is it? Is it a? Is it a transformation? That is it a transformation like rotation or other things that could be applied to a given configuration? Shit, okay, okay. G is a group of symmetries. Group of symmetries. Why group of symmetries? Why are you calling it group of symmetries? I think that is the accepted term to refer to this thing. Group of symmetries or transformations. Group of transformations seems much more intuitive than group of symmetries, right? So we have, wait, what do we have? Yep, we have 4 hours. Yes, we have G. G is a group of symmetries or a group of transformations that you can. Okay, shit. You are saying this is a group of symmetries. Group of transformations that are considering just a group of configurations which could be converted into each other using the transformations. G is a set of transformations together with the rule for combining them, going one after the other. G forms a group. Identity doing nothing is included. The configuration stays the same. Closure doing two transformations in a row gives another valid transformation in G. I don't get it. Is G a group of is G a group of transformations or a group of configurations that could be each other? What is it? Okay, two responses. Uh, that is a sharp distinction, and it is exactly the kind of thing mathematicians obsess over. The answer is G is a group of transformations, symmetries. Why are you calling transformations as symmetries? Why are you referring to transformations as symmetries? Not a group of configurations. Okay, that is clear. Okay, we will have to talk about this, but before that, let's unpack what G is. G is a set of operations. You can apply configurations. Example, for a square, G equals identity, like no transformation, rotate 90-degree, rotate 180-degree, rotate 270-degree, and reflect vertically, reflect horizontally, reflect diagonally, reflect anti-diagonally. Okay, okay, that makes sense. That makes a lot of sense. G is a set of operations that could be applied to a transformation. These operations form a group under composition, doing one after the other. So we don't just have to choose one of them. We can create a subset. Every valid subset of this is a valid transformation. Okay. And every valid subset in any order, if we apply it to a configuration, the resulting configuration is also a valid configuration. Okay. What configurations do? Configurations X are not part of G. They are what G acts on. Okay. Okay. Each transformation that belongs each transformation G that belongs to G takes a configuration and maps it to another configuration. Okay, shit. Okay. And not just every individual transformation, but every subset of G maps it to another configuration. Some configurations may map to themselves. Those are fixed by G. Those configurations are this transformation, identity transformation, when you do not do anything. Some may get mapped to different when those are in the same orbit. Okay, so should G is a set of edges. G is a set of edges like that, and the things that it connects are configurations, and there are also loops. And what we essentially have to find is the number of components that we have. Okay, some configurations may map to themselves fixed. Some may get mapped to a different one. Those are in the same orbit. By being in the same orbit, you mean, what do you mean? Orbit, viewpoint, your intuition. You're thinking maybe G is a set of configurations that can be converted into each other. That idea is actually called orbit. Okay. Orbit is a technical term for this thing. Makes sense. Orbit is the technical term for all the configurations that could be converted into each other using any of the transformation in the set G. Okay. An orbit is a set of configurations that you can reach from each other by applying elements of G. One-sided lemma counts how many orbits there are. That makes a lot of sense just by having a clear notion of what these terms refer to. So your intuition about group of configurations that could be converted into each other is actually describing the equivalence class orbits. Okay, now you are using in the word equivalence class. Okay, equivalence classes orbits under the action of G. Analogy. Think of G, a set of buttons you could press, configurations, pictures on the screen, orbit all pictures you can reach from a starting picture by pressing some combination of buttons. Okay, now I have a question. Why are you using the word symmetries here? Okay. Yeah, yeah. Why are you using the word symmetry and transformations interchangeably? Why do you do that? I am using them interchangeably, and there is a reason. But it is worth being precise about what is going on. Okay. What is it? What a transformation is? Transformation is any rule that takes a configuration and produces another configuration. Yes, rotation, swap, and this. Okay, so they are symmetry. What is a symmetry? A symmetry is a special kind of transformation. A transformation that preserves the underlying structure of the object you are working with. That is like if I have a square, I can rotate it, flip it, do anything. If I have a circle, I can rotate it, flip it, or do anything with it. The transformation is symmetric. For example, rotating a square is a symmetry because the square still looks like a square. Stretching the square into a rectangle is not a symmetry. Yep. It breaks the squareness of the square. Squareness. Okay, squareness is a mathematical word. Why they coincide is Burnside's lemma is used to count configurations up to equivalence, where equivalence is defined by the orbit, where equivalence is defined by some set of structure preserving transformations. Yes, structure preserving transformations. So the transformations we consider in G are always symmetric of the underlying object. Nicholas, no, they don't change what counts as a valid configuration. They just move it around. That is why in this context, symmetry and transformations are effectively the same thing. Transformation emphasizes the action on the configuration. Symmetry emphasizes the property of preserving object's structure, but object's structure is not being preserved with any given transformation from G. It changes, and you just said it yourself in the last response. Where was it? Where was it? Uh, or where it might stay wherever it is, or it might go to some other object. There was another answer for this. Orbit viewpoint. Yes, some get mapped to different ones. Yes. Yeah, how do I select it? I prefer this response. Yes, this one, this part. So here you said that some transformations may change the original configuration to some other configuration, and thus the symmetry is broken. So G is not a set of symmetries. So G is not a set of symmetries, right? Let's be careful with the language here. Okay, I will not abuse you. When I say some configurations may get mapped to a different one, I didn't mean the symmetry is broken. In fact, the whole okay. The properties which are being kept, which are being preserved through the transformations are not the fact that they are part of the same configuration, are the properties which define that configuration as a valid configuration. Okay, I think that is the thing. What you mean? Okay. By symmetry, the properties that are being preserved through a transformation here are not the fact that they are the same configuration configuration, but the fact but the properties that makes a given configuration a valid one. I think that is correct. Exactly, you got it. Okay. That is the subtle but crucial point most people miss the first time. Okay. What is symmetry means here? When we say G is a group of symmetries, we mean each transformation G belonging to G preserves the structure of the space of positions, the rules of the game. Yes, you do not break the game when you are considering different rotations and things for a square. After performing every transformation, you make sure that you have a square. You do not have a circle. Like your square should not become a circle or a rectangle. That is what they mean by symmetry. Okay. It does not mean that every G leaves every configuration unchanged. Here, instead, it guarantees what it guarantees is if a configuration was valid before, it is still valid. Applying G, the transformation cannot turn a legal configuration into an illegal one. It just permutes the positions in a way that preserves adjacency, arrangement, or whatever rules are valid. Okay. That makes sense. That is what they mean by group. So group is a group of transformations that we can apply on given configurations, and those transformations are symmetries in the sense that when we apply those transformations on a configuration, the configuration is still valid after making that transformation. Okay, at least we understand the question. Now we can maybe we can go and see what the solution is. Okay. I think it's been long enough already. Yes, 4 hours and 15 minutes. Okay, we understand the problem. At least we have a group. We have a group of, we have some configurations which are valid. And then there is a group set G which has some transformation rules. And every transformation rule is a symmetry in the sense that that rule converts each of these configurations either into some other configuration, or this configuration and this configuration remains the same as it is, but the symmetry part is used here because this any of these transformations, if you apply them to any of the configurations which is valid, that valid configuration is still valid after applying the transformation. Does not matter if that configuration changes into some other configuration or remains the same configuration, but the symmetry part refers to the fact that after applying this transformation, The configuration is still valid. Valid. Okay, makes sense. And I guess I can rest now. It's been 4 hours and 15 minutes. And this would be the end of today's stream. And thank you for being here. Bye.